So in the previous class, we did talk about LoRa and QLoRa. Basically, there are two ways that we can basically fine-tune large models and like efficient, basically fine-tuning. Now, we're going to start basically first talk about some of the limitations that this pre-trained encoders they have, and the overall, the encoders are pretty strong. They learn lots of contextual meaning about the data. They have a really good way of understanding the language, but they are really bad at generating anything that comes to generation. Despite the fact that they have learned the context, the features and stuff like that, they still cannot help with the generation. Now, there are a couple of extensions of the BERTs that researchers developed that they were like, okay, let's improve BERTs. See that if we can basically make it more advanced, if BERT can generate more data, or even if we could increase the accuracy that BERT has. By default, if you remember, what happened in BERT was there was two tasks. One was the mask modeling, which you basically mask words or basically replace words. So the model needs to predict those. And the second one was that next basically sentence prediction to just predict if this sentence follows the previous sentence. So there's a basically algorithm called Roberta, or the paper basically. And what they did in Roberta was they removed the next sentence prediction because I was adding complexity to it. And they basically just let BERT to train for a longer period of time. And it got a much better performance in compared to BERT. And so there are a couple of claims that they have, but the main concept that they did was that, hey, we don't need to predict the next sentence. We just need to provide it more data and give it more time to learn. Okay. The next one was a span BERT, and the span BERT, the idea is more interesting. Overall, if you hear the term span, so if you have a sentence like a word one, word two, and so on. If you pick one word, that becomes a span of like one. If you pick two words at the same time, it becomes a span of two, and the span becomes this window of consequence or basically sequential words or pixels, for example. That becomes the definition of a span. In a span BERT, the idea was that, hey, instead of dropping one mask, two masks, we drop series of like words or basically tokens. Like we call here, as you can see on the right, they basically did mask, 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 mask. And the model basically needs to predict all of this, not just one word at a time, actually kind of like a longer sequences. So the idea was that, okay, hey, maybe this way we could generate, tokens, because if we can mask for larger amount of basically or longer amount of data. Now, so this is just the same thing in Roberta. Then it came to the decoder idea, and the idea in decoder was that, okay, well, encoders, they couldn't generate tokens, they couldn't do anything like a translation or anything that it's kind of like you need to do generation. So let's pre-train the decoders, and the idea of whole decoder was that we have seen in the transformers is that you have a similar structures of transformers, and then at the end you basically, so if you think about the encoders for training, you give a word, you predict the same word, right? And then you give another word or something, and then you predict something related. So it's kind of like a direct. In decoder, you still do the same thing. However, there is this mapping. The output now becomes the input back to the model. So it's kind of become next token prediction, right? Because you kind of is sequential. So these tokens, they can easily impact what the next one is going to be for generation. But in encoder, you just do direct translation. Like you don't care about what's the next one. It's just right now, this token is my task to predict. So now for decoders basic application, for example, anything that you want to do dialogues, or if you want to do summarization and stuff like that, the decoder is good because it not only understands the context as an overall, but it also because it can generate new language, it can do summarization, it can basically describe something for you, but encoder doesn't have that capability. Encoder can be used for searching, like say that, hey, what does the content of this document look like the content of the other document? You can do something like that because encoder is really good, but you cannot ask it, hey, given this document, summarize it for me, or given this document, tell me what you saw in it, because it's not good in, it's not coherent in generating the how to explain or generating the language. Now, the overall, basically, if you think about the GPTs, the first basically, so the term GPT, yeah, it still actually debates if actually what it means. Generative pre-trained transformers is kind of like an assumption, because in the main paper, it actually doesn't say what's GPT. So the assumption is that it's either a generative pre-trained transformer or generative something token, something like that. But I'm not sure. But so we don't know actually if it's GPT is generative pre-trained. Just we call it GPT. So the first one was 12 layers, 117 million parameters, like 768 dimension. And then basically the feature one, the last layer has like this really long vector, as we know to expand it basically. And the way that basically, one of the ways basically you can basically do language inference, you start with some starting token, you put some premise, and you put some separator, you call it the line, and then you put some hypothesis and extract it to get the output. So this basically means that, imagine I say here that he was in the room, or he was in the room, and so that becomes, no, he turned off the light, turned on the bedroom light. And the hypothesis becomes like, he was in the room. And the model needs to answer that yes, for example. So that's the idea. There's some information given, some hypothesis, and the model needs to, from the information, validate that if that hypothesis is correct or not. So that's just one scenario of what you could do. Then it came the GPT-2, basically extended the overall the GPT. They've made it larger. So one thing that about GPT-2 was that it becomes more coherent in generating language. So the GPT-1 language wasn't really coherent. It wasn't like that. Well, GPT-2 start to kind of make more sense, like kind of like look like humans. That wow, they can generate text and stuff like that. Then it came GPT-3 and the concept in context learning, and so GPT-3 again larger model, but the in context learning is that the model is capable of learning something without any retraining or any updates, basically, using the general knowledge that it has learned before. So if you have a really good model that has a good knowledge, all you need to basically is to, for example, I want to, and we will see something like that. Like you say, I don't know, hello, and in Farsi, for example, if I say salam, and then I could pass another word in English and don't give the answer and just let the model predict it. So that comes in context learning. So the model has that domain knowledge, and it just needs some sort of like a guidance. Okay, hey, yeah. So that was one of the biggest things GPT-3 had, that without training, you could actually, from the domain knowledge it has, it could actually do new tasks, new things. Then it becomes like, okay, GPT-3 is so cool. Everyone like, okay, let's build upon it, right? Just because you can do so many things with it. Now, the idea came out, okay, we want to adapt GPT models. And I don't know if you remember, like it was 3 years ago, then ChatGPT becomes something and everyone start building upon it, right? And the idea was that, okay, how could we optimize? How could we use it, right? So they are basically, this is released by OpenAI themselves. There are basically two axes that for retraining or basically refinement of this model you can take. One is that comes around the model optimization, basically. And the other one is around the context, basically, optimization. So you've got two axes that you can go. Either way, the recommendation is always is that start with prompt engineering. That's the bare minimum things basically you could do. You don't need to fine tune. You don't need to do RAG. Try basically prompt engineering, and basically you work in this region, and you do a different prompt engineering that we're going to see. You try those, and if they didn't work, depending on what's the task that you need to do, you basically go either up or you go to the right. So that was the idea of prompt engineering. Then we have the idea of RAG. We're going to talk about this in details. But the idea of RAG was that, well, the model is pretty good in the general knowledge, but what if your user or the customer has some specific types of information that the model actually doesn't know? Either private or the model's general knowledge is not good enough. The problem with GPT model is that they are generative text. Their job is autoregressive to generate text, correct? So they will generate text, and that's what becomes hallucination. Everyone's like, oh, it's hallucinating. Well, yes, but also the model is trained to generate text, so it will generate text. So how could we help this model to produce something that actually makes sense? One way is that, well, probably do RAG. And the RAG is that, well, instead of just basically confining the model to the general knowledge it has, you bring some knowledge and share with the model basically to provide the answers. We're going to talk about that in details. So maybe from here you go to RAG and you try basically different types of RAG to see if you could optimize, you can get the answers. If that didn't happen, then maybe you go, for example, you do something like fine-tuning. And again, it's all like again objective to whoever is working on it, or how much money or time you want to spend on it. And you go on fine-tuning, because the idea of fine-tuning is that you change the model parameters. You just more like you go directly over the model itself. You optimize the model. However, in the vertical axis, the y-axis, you actually focus on the knowledge that the model has, not the model itself, basically. You don't change the model parameters. So, and then you can actually jump in between to do series of this to basically to optimize your model. And the last one is that you can do all of the above. Like you can, there are scenarios you do all of them. There's a really nice video by OpenAI that they go over this chart and they talk about it. If you search it, it's short. Definitely watch it. They give some examples of customers that they actually did all of the above to figure out what's the best scenario to improve the accuracy. None of those work at the end, and then they find out it's different technology, a different approach to basically get a high accuracy. So it's all of this is possible, you know. So it's kind of it's not a free lunch theorem that you think if I do this I will get the answer. It will work. Now, so what we will do, we're going to start with RAG, and then we will basically, because that's just a couple of slides, and then we will go over different types of prompt engineerings, and then we go over the fine-tuning concept. So now, what is RAG? Retrieval Augmented Generation. The idea is pretty straightforward. It's, well, we know the model basically hallucinates or generates fake, or not basically, generates things that they don't make sense. They might be coherent in the language, but they are not factual. That's the correct way of putting it. So instead of doing that, what we do, let's say we have a bucket of knowledge that we want to be sure the model only answers from those. So the idea here is that you bring that bucket of knowledge and you condense it into some vector representation that is like a contextual representation, similar to what we have seen before as part of the encoder, basically. You know, you pass it to a series of encoder or an encoder, and that encoder gives you that contextual representation of the sentence. You store that contextual representation of your sentence in somewhere, some library, for example, which is technically a vector database. And when a user basically comes and asks a question, you need something here. Here it says a smart retriever. It's technically just you just need a model, or not a model technically. You just need some sort of like a code that gets the user's question, converts it to like a vector representation, and it does a search, make a call to that library or that vector database that you have, says, hey, given this vector representation, what's the closest vectors that you have to this? Right? So you extract series of vectors back from the library, and then you bring those vectors, combine it with the query that you receive from the users as like additional information, pass it to the LLM, and the LLM, given the query and the basically additional knowledge that is appended to it, basically, it generates text. So that way you basically help the model to be more factual, because it already knows the context, it knows the query, and it knows the context. This is I have this domain knowledge, right? So it helps basically to a great extent, prevents model from generating basically unrealistic answers. So now, there are two main components in RAG. Basically, is the retriever and is the generator. Okay. So the retriever basically, again, is just a search optimization technique. It's kind of like I need a model or I need a piece of code or search algorithm that could do a great job in searching for me, you know. But also, you also need some embedding technically. You need some encoder that you pass a sentence to it, like a bird or some sort of like a pre-trained encoders that you pass the documents, you convert it to a fixed, basically, vector length for every sentence, basically, every query that you receive from the user. Then it basically goes to this, like a database that it has, and it searches for this vector to see where I see something similar to that. And you retrieve those information, okay? Now, we're going to talk about how we create this, but overall, basically, that's the architect, you know. And then after that is just a GPT model that next token prediction. Now, there are some challenges, basically, and advantage that the RAG has. Well, advantage is that it improves the factuality. It's really useful for types of information that is domain specific, or maybe there's not a general knowledge that the models have. And it reduces the need for frequent fine-tuning. Why? Because if you have a RAG-based model, you don't technically need fine-tuning. Every time new knowledge comes, you just need to add it to your knowledge base. Instead of focusing on the model, you're just focusing on this part, right? There are challenges with that. The challenge is that, well, it's a search optimization problem here. Every time you get a query, this might be a really large database, right? So you need to be sure that you have a proper search technique that can search within a really short period of time that can extract the information. Otherwise, user waits for a long time for you to try to find something. The other one is that, you know, it also depends on the quality of what you find. You know, it's like you might find something where it's a good answer that you find or not. It's also a problem. The scalability could be another problem. The embedding itself could be another problem. The way that you embed these sentences or these documents, it could be a problem. The other thing is that, so when you want to create this database, you normally have large documents. The problem with these large documents is that, well, if you want to convert this to a vector representation and store it here, you cannot just convert the whole document, because all of these models, they have a fixed length vectors, right? And also, even if you try to convert all of this, the problem is that it's not going to carry the detailed information maybe that you want to see. Maybe it just has a really general idea about the document. So there are a series of pre-processing that you need to do is, I think the first one is beside the cleaning and stuff like that, you need to do something like chunking. You need to find a proper way of chunking these contents. You know, chunking could be like, imagine you go over the course slides and you're like, well, it's easier to chunk. Why? Because there is a header and you're like a subheader. So I can chunk based on headers. Within a header, I can chunk maybe based on subheaders and have like that. But what if the document doesn't have that header or subheader risky architect? Then can I just chunk every 256 words? What if I break the meaning of the sentence? You know, it's kind of like so that chunking part is itself is kind of important. So you need to be sure that you could either chunk based on, you know, I don't know, like a structure. You can do hybrid chunkings. There are different techniques people apply, but overall, it's going to be important. So you basically have the documents, you break them down, and then you convert them to the chunks to some basically vector representation embedding. But you also need to, for every chunk, you need to create something called metadata. So in any ML system, when you build something, you basically have a series of like artifacts generated around the data, like the time of generation, page that it was, and stuff like which document this belongs to. So you need to create series of metadatas, which makes it easier for retrieval, right? So so here basically you have this indexing, you know, that comes from the database concept. So when you have this data and you want to index it, so it makes it for search. Later you want to search, so I can index, I have the access to the index, I can get extract the basically data. But you also want to be sure that not only you have this like embedding, you also have proper metadata, so you can map it back later to whatever document, whichever page it is. So that vector DB that you have is going to have metadata, and you're going to have embedding, and you query against it. You get series of answers, because if you do, for example, with the things that when you do search and you get answer, probably you don't want to get just one answer back. Normally you do K answers back, for example, like 10 maybe, like a response back, because you have 10 are really similar to that document. So you don't get just one, you basically pick multiple topics and you pass those multiple topics. So there are a couple of ways that here you can play around. So there are some approaches that you get multiple topics instead of passing all multiples to the decoder. You actually have another model here. It's kind of like a critic or ranker. What it does, let's say I get 10 answers back, and there's a model that does ranking and goes across this 10, says that from this 10, only top 3 I'm going to pick. It's like a supervised trained model. So it's just, and every time says this top 3 and the rest goes out. Or it could be a model that just says, I want one answer, so it's kind of like a classification. You pass 10 vectors and it selects one and says that this one should go forward. So there are different ways that you can do this extraction, but that's the overall idea of RAG. So it's an easier lift from perspective of if you have the good data that you want to use, like, and also you have a proper knowledge of how to do some text cleaning and how to do some chunking, and because it requires some lift from the engineering perspective, right? Any question on that? Straightforward. All right. So then it goes to the prompt engineering, which we have all sort of like a prompting these days. Some of those are working better than the other ones, but we would just try to cover some of those. But the idea of prompt engineering is that your goal is that instead of trying to pass a new data to the model, or if it's like what we do in RAG as a knowledge source, or instead of trying to tune the model, you try actually to tune the way that you ask or interact with the model. So that's the idea. You want to be sure that you use the way we know these types of models. They have a really good general knowledge. We want to find a way to basically utilize that. Is the way that we interact with this. We have one person here. The first one is zero-shot prompting, which the idea of zero-shot prompting is that, well, means that zero-shot prompting is that you actually don't provide anything to the model. You just, the model has some knowledge. You just ask a question from the model. You say, hey, what is this? Right? So that basically you prompt it to give you an answer. That's a zero-shot basically prompting. So you don't pass no information. You just ask your question, and the model basically provide the answer. The next one becomes few-shot prompting, and here is basically that scenario is that you want to be a bit more specific with models, so you provide multiple examples, like a few examples to the model, and here, for example, you say you tell as a prompt, you write a great product, 10 out of 10, and in front of you say positive. Didn't work very well. In front of you say negative, super helpful, worth it, positive, and then later you write it doesn't work, and you don't give the answer. So the idea here is that the model basically learns that what you mean based on the context that you provided as like a few examples. Okay, sorry, I need to. All right. So, it's a great point. Good. recording. Yeah, okay. So that's the idea of few shot. Then we go one level further. It's called chain of thoughts, which these days actually is becoming more popular, especially. And the idea of chain of thought is that when you generally ask GPT models for an answer, they were trained for generating. And they just one token at a time. And they're actually sometimes, basically they're optimized to even producing a faster result. So it's kind of like sometimes they jump to conclusion so quick. The idea of chain of thought is that you encourage the model, but this doesn't. You encourage the model that, hey, take a moment, think, break down the question, and then basically provide the answer. So on the left, basically, it's like a standard prompting. You give a prompt, and the model quickly gives you an answer. On the right, I have a chain of thought. You ask a question. Here it says, Roger has 5 tennis balls. He buys 2 more cans of tennis ball. Each can has 3 tennis balls. How many tennis balls does he have? First, as a prompt, you give an answer that Roger started with 5 balls, 2 cans of tennis balls. Each is 6 tennis balls. 5 plus 6 equals 11, and the answer is 11. So you give this example, but as part of this example, you show the model how to think, how to break down the problem into steps, like how we might solve it. And the idea will be that when you ask a next question, the model basically tries to mimic the same thing. It's like, okay, I need to break this down into multiple steps and then try to solve it. You know, so that's the idea of chain of thoughts. Then there's a technique called self-consistency prompting, and it's pick the chain of thoughts and do ensemble model on it. That means you ask the model a question. Basically, the model asks the same question from itself like multiple times, and it does a majority vote, and it gives the final answer, right? Because it's a generative model. Every time you ask a question, it gets a different answer, right? So in general, basically prompting, you might just, if the model just answers one time, it gets a wrong answer. But when you do self-consistency, the question goes to the model, maybe ask 3 times to produce answers. Then you do majority votes. Here 18 and 80 is a majority vote. Then you give the answer to be 18. Of course, it's more computationally expensive because you need to produce that. But it helps with having a better, basically, results. Then the next one is called like instruction-based prompting. And instruction-based prompting is technically what you want to do is provide some instruction of what you mean to do, like translate English to German, and then you give your sentence. So like you just give an instruction, and you give basically the question. Probably that's what you do when you go to ChatGPT. Give me the solution for this homework, right? Just gives you that one. Yes.
Question about the self-consistency prompting. Yeah. You essentially said that the model answers the question internally multiple times, and
so model doesn't answer. You basically ask the model multiple times, basically.
Oh, okay.
So it's like what it means is that you get a prompt. You basically make 3 API calls, the same model 3 separate times, and you get the answers, and then you do aggregation. Right? That's what it means. Not model doesn't do an internal phase. So instruction-based prompting is you just provide the instruction, and you give a prompt, and the model gives you some answer. Then there is this technique called persona-based prompting, which is actually quite interesting. I tried it recently. I'm going to talk about it. But the idea is that in general, idea is that whenever you ask AI a question or ChatGPT or any of chatbots, basically it's single persona. You just say that, hey, I have a question, as an AI assistant is helping you. The idea of basically multi-persona here is that, well, you create these personas, like one is an AI expert, the other one is a math expert, the other one is this expert, and so on and so on. So you create as part of your prompt that these are different personas that exist here. And you basically ask a question, and you prompt it that these personas are going to interact with each other like this. That becomes multi-persona. So one of the original paper of multi-persona, they have really nice examples in it. I upload the paper to read. A couple of them is like you basically let the models to interact, to talk with each other. So you create a persona that says something, and the other persona gets it as an answer, answers back to the model, and the other then every persona basically holds a conversation, right? Now I did a couple of days ago did a test with one idea on this multi-personas, and I wanted to search about something, and I asked this ChatGPT, you are, for example, expert researcher, and you do a great research and stuff like that. And then I say that there's this other person who's this top columnist in New York Times, who writes the best, basically, articles. So you always do a research and you provide the research to this person. This person basically gets research, write a really nice article and provides this to this other person that creates an HTML does it. And it just exactly does the job for you. And it's like if you do it in one prompt, it gets confusing. But when you let this to interact with each other, it's actually end up being really good. And every one of those actually, so also you can basically prompt it to give feedback to each other. So you could have one that sits at the end, which reviews and gives a feedback to the previous one. I don't like it, go fix it, and stuff like that. So you can create this loop of prompting, which it's interesting to play around. So this becomes an example from the paper that I was saying that. So you basically have this prompters that AI assistant, game designer, Harry Potter fan, Games of Thrones fan, and so on. And you define some remarks about the collaborations. Basically, you then decide this how the collaboration basically starts. The AI assistant starts with like that, and the other one review. They provide some feedbacks. This one gets the feedbacks, updated from those feedbacks, and continue, and it produces a really nice, basically, generation, basically, sentence. So that's the idea of multi-persona. Then it comes the AutoCAD, basically. So the automatic chain of thoughts. The idea here is that could we enhance or basically create this chain of thoughts automatically instead of basically we kind of enforce it, let the model basically learn itself. So the way that they have done it is you bring this bucket of queries that you have, and then there are actually a couple of steps in it in the paper, but I think the overall what they did is like you have lots of queries. You bring these queries and you do embedding over them. So now you have these query embeddings. These are all like vectors, and then they did clustering. These are like a vector, so you can do clustering across these vectors, and you create maybe, for example, this is like unsupervised series of clusters. And you have, let's say here we have two clusters, and every cluster basically has a centroid, right? For example, center point. You sort the queries within every cluster based on how close are to the center point. So now you have two groups sorted basically queries. So that's the first part of the model that they have, which is this part, right, on the left. Then what they do here is that, so you bring that, those basic clusters for every query, and you add this basically prompt, let's sync step by step to those queries. And then you pass, now you have a sorted cluster queries with the prompt attached to them. You pass those to a zero-shot chain of thoughts model, a model that is guided to have thoughts, like break it down, but zero-shot without providing any examples. So you pass it to that and ask the model to provide something called rational. Rational is the steps that you taught in order to give the answers. So the model gives you two things: the rationals behind the decision and the final answer. Okay. So now you have, for every clusters, you have you have queries, that prompt that says, let's think step by step. Then you have rations, and then rationals, and then you have final answers. Then they have defined a way of, they have defined some rules. So this is the main steps in the algorithm. And again, just quickly, as you see, it's just exactly what we talked about. You pass this to a bird, sentence bird, you do a clustering on it, you basically sort the clustering based on the distance to the cluster center, you return the clusters. And then you bring the clusters, you pass it to where does it say? Zero shots cut for every element in each clusters. And you say that give me an answer and a ration, and you put those all together and we return it. Now, the next step is it's kind of like decide which one you want to accept, which one you don't want. And what basically they did here. So they have this selection criteria, for example, is that if the question basically length has no more than 60 tokens, basically they keep it. If the ration contains no more than 5 reasoning steps, basically they keep it. That means if it becomes too many steps, too many loops, you don't accept it. So they have some selection criteria to accept those. And that basically becomes autocad. Without a need for you to tell the model how to think properly, the model learns basically how to do it. But still, it's kind of like you define those decision criteria, like what is a good or what's bad, you know. But that was the main idea. Any question on that? Yes.
So for all this prompting techniques, we don't touch the weights, right? We don't.
No. That's the thing about prompting. So you don't touch the weight and you don't have the RAG concept. Like,
so let's say for few shot, for example, I provide like few examples, but how does the model learn?
So it doesn't learn. There's no learning in any of these techniques. The base model does not learn anything. It only, when you go on a chatbot, for example, you have this context that the session that you are in it, and every time you basically ask a question, I don't know how these actual platforms work, but I think the idea is that they have this summary of whatever was previously in the session, and every time you ask a new question, they have the like a vectors of that added to your new question, pass it to the model. So model at every moment has a history of what you have been asking and what's the new question and what's the general knowledge that it has. It never, and after you're done, that session information is gone. However, for example, in like platforms like some of the like ChatGPT, if you go and ask the ChatGPT, previously we have talked about this, go extract that information. It doesn't have a session information, but it has history information. So you can go search against your history, right? But again, that's all. So they can keep track of what you have been interacting or asking, but there is no update. There's no learning based on what you are basically saying.
So let's say the example you took, a persona-based prompt. If I want to implement that on my model, like I download a model, I have my local model. How do I implement like these kind of techniques?
So you have let's say you have a local model and you prompt it, right? So as part of prompting, you basically, as you write in your prompt that, hey, prompt one basically is that you are an AI expert like this. And then you say that you are working with this second person, like you add a second person, a third person. Then you have an instruction of how they are working with each other. Right? So in the paper, like if we go back here, so the image here, that's the part you see that so you first define this personas, then you define basically, so you say that the NPC should be a character that reach from this. So that's a remark from this person. Whoever is this is like a game designer. Harry Potter fan says that the incantation of the Patronus charm in Harry Potter is this, right? So they give you some information, then you do the collaboration. So you have the chatbot that gets that information from this guy, says that thanks for the information, here's is my draft based on that information. Then this guy is reviewed and says that if they like it or not. In reality, all of this, they are the same model. They have the same general knowledge. There's no learning here. And you just, because the problem is that it's lots of knowledge. The model, if you don't guide it, it can easily diverge from the actual answer that you're asking. So this way, you basically put the model in that persona that you are this. So maybe from the model's perspective, I don't actually know how the internally works, but maybe it's like that when you say that you are a game designer, model only in order to generate answers, only looks at that the part of the brain, if you think about that's only for
Direction of.
direction. That direction is for game design. So it makes it easier for the model to give answer with respect to that context. But then again, there won't be any updates.
And also in RAG, there will be any, it's just giving context.
In RAG also, there is no model training. It's context optimization.
So I'm just wondering, just for fun, what if I say that one of the persona is to create other personas? Can I try that?
Yeah, I mean, actually, there are a couple of cool ideas like that. You can definitely do that. Also, there is a notebook LM by you know it produces like the what's called podcast, right?
Podcast.
I actually play with that around. I actually was planning for this class for every week. I was planning to put a podcast for you first for you guys to basically listen to, so you know what's going on. Yeah, so that's an idea where it becomes like a multi-persona interaction. So it's like you just give them an overall idea, and it's that it converts that to between 2 or 3 or multi people that they are talking back and forth with each other. Yes.
How is multi-persona different from agentic behavior?
Multi-personal agent. So I think the first thing about agent is that it's kind of like a really vague terminology these days. Like everyone through agent. Like I have been, to be honest, with in places that we say that we have agent, and it's like what type of agent was like. I don't know. You can ask ChatGPT to open a calendar I don't know, like a what's it called, calculator for me. And that's not an agent. It's just it has a tool that it knows how to open a prompt for you, right? So if you are saying that multi-agent from perspective of I have these specific tools that they are doing a specific task based on the prompt that they are receiving. So the agents that you have, they are opening something, doing search for you, right? Correct. So they are specific for a task. The idea of multi-persona is that you just work with the chatbot, and the chatbot is just generating text for you. It's just we basically say that, hey, I want to interact with each other in order to give you a more coherent, more detailed answer, right? In agentic ideas, and again, I might be wrong in this, but I think the agent idea is that you want to have a series of tasks that repeats a lot, and I don't want to repeat those tasks. I can automate those tasks like by giving it to some tools that they can basically take care of those for me. Versus like in agentic idea also, you don't need to, like if you define, like actually I was doing this week, we were trying to create a Google Calendars, GCP, an agent that basically guides you through GCP how to do installation on things, right? So it's like what it does, it opens basically when you run it, it opens a Google Chrome for you, and it says that Google Chrome takes you to a GCP page, and it tells you log in here, right? It's like a guidance, and then you log here. After that, it tells you go click here, create a project. I was working on something like that for a project, and when you have something like that, you put the steps correctly, and say that this is what's going to happen, right? So there's no deviation. Technically, the agents are really defined on what they're supposed to do. And the idea of multi-personal chatbot is a chatbot. It's an interaction. You know, there's a feedback. You take a feedback, like if one person gives a feedback, the other one goes based on that feedback, updates the result. In agentic scenario, you don't want that to happen. You want to be sure that your agents basically they work really good, right? I was about to talk about it, but I'm going to just say it. So imagine you have 10 agents that they work together. So I have 10 agents that are working together, and every agent has 95% like a chance of success, always. Okay, I will leave this for you guys to give me an answer. What is the overall chance of success for this AI agent system? Okay, I leave it for you to think about it and just get back to me after the class. All right, so it's like, because agent, you want it to be sure that they are actually doing really good job. So you have 10, each one of those 95% success rate. What's the overall chance of having a system that works?
How are they interacting?
Was that?
How are they each interacting with each other?
So, sorry, let me give you a better context. in order for this system to success, all the agents need to be successful. If one agent fails, that is a failure. Okay, so that's an additional context. All right, now let's go.
Their success are independent.
No, they're dependent.
One fail doesn't mean the others fail.
Yeah, from that perspective, they're independent, but if one fails, the whole system counts as a failure. Okay.
So in auto chain of thoughts, when we say clustering of questions, so how do we cluster those questions? Like, do we,
So you have an embedding, right? Just do some sort of k-means, for example. Right, it's to a technically higher dimension, so it's kind of like more expensive from the.
so that is done like in the model itself, that is not done by the prompt.
No, so that's a great question. So the AutoCAD, it's a system, is not just an LLM. It's a pipeline of the steps that you do in order to train or basically have basically whatever types of model that you have, definition that you have here. So let's say I have my pipeline starts with data comes through, data goes to a bird. That's what they say. Data goes to a bird. The output of the bird is a vector representation sentence, basically they say, the sentence representation. And then you convert all your document and you have this vector representation for all your documents. Then you do some sort of unsupervised clustering, okay? I didn't read the paper fully to see that what's K they selected or stuff like that, but I assume that, you know, you can do some sort of like, I don't know, like cross validation to find if you want to pick an optimal K or something like that. So they find a couple of Ks and then based on that now they have clusters. Every cluster has a bucket of documents in it. You sort the documents based on the distance of items in the cluster to the center of the cluster, right? And then you bring that out. So that first part of the pipeline is done. Second part of the pipeline is that there's some general API pre-trained model GPT. You make a call every time you pass, like you have, let's say here you have 2 clusters. Every cluster has 5 queries in it. So you total make 10 API calls. Every time you make a call to this the pre-trained model and you have the question, you add to the question, let's sing a step by step, and you pass it to the model, and the model is supposed to basically do a 0-shot chain of thought. So the model provides you the thought process, and the final answer. So you bring all of those and you have this final data set, then you have some selection criteria, you go over those and you select this. So now you have a way to generate chain of thoughts data, you know, using some model and without you creating this. Your model basically automatically is like unsupervised using clustering. And again, that although the selection criteria is like something that you have selected.
So in this case, when you mentioned that each cluster has questions and queries, right? So are they generated by a domain expert?
No, the clusters, the queries, there's just query that comes through. There's no
User query.
Yeah, so there's no good answers here. I don't have an example of the data that they used, but it's just a user query basically that can be part of the query. While shopping for music, Zoe bought 3. So like the overall question that says Zoe bought 3 discs, and then later Zoe bought another 8, and so on. And then said, what's a total, for example, number of discs that Zoe has?
But those clusters are like pre-made, right? When you're doing like clustering.
No, they make it. It's like unsupervised. So you learn those clusters.
A bit related to instruction-based prompting. So this is kind of something I faced some time ago. I had to solve a couple of around 10 questions, and so what I did was I gave the basic ChatGPT model 10 instructions saying these are the instructions I want you to follow when solving these questions. I gave the 10 questions. For every question, it followed a different subset of the 10 instructions while solving the questions. Like at that time I didn't think much of it. Now I suddenly thought of that.
So you say that you passed 10 different instructions?
10 different questions. For each question, it followed a different subset.
Combined, you basically said. Did you pass those instructions first, then question first, or like every question and the instruction together?
10 instructions, 10 questions.
Maybe try to see that if you just put one like question, instruction, basically then next question, instruction.
I wanted all 10 instructions for each question.
Oh, you wanted to combine?
Yeah,
Okay. So,
but it did a subset of the 10 instructions for each, a different subset of the 10 questions on each question.
don't know what to say, to be honest. It's kind of like an engineering thing, you know, it's kind of, you need to play around to see exactly what's that prompt, like what's the model is receiving. But it's also, you know, the thing about prompting is that if prompting was actually that straightforward, we didn't have this many prompting techniques. It's not working. It shows that it doesn't work. It works for something, it doesn't work for other things. That's why we need to keep at different ways of prompting.
But maybe I feel like it depends on the domain as well, because the instruction may not be valid for that particular question. So maybe
Yeah, that's the whole thing of engineering it. You when you engineer the prompt, it might make sense to you, but from the model's domain knowledge, like that might not be correct prompting. Great point. All right. So the other thing now is comes that, so those are like the prompting, and then now we go to instruction tuning. Okay. So so this is no longer prompting. So here basically we try to tune the model. We try to basically somehow like update the models here. So in the instruction tuning idea is that you want to provide model with a proper data set of instruction and how it should respond to those instructions. And you want to fine tune the model basically, like do a supervised fine tuning basically based on that data. So it starts by creating a data set. So you create a data set of text. You have these labels. You have some templates. You create some instructions overall. So this part is handmade. Then there is also this model, like ChatGPT, for example, they did, and they use also more instruction using ChatGPT. So handmade instruction, model-made instructions. Basically combine those, you pass it to LLM, like you have a large amount of instruction, and you supervise fine-tune your LLMs based on all this instruction and the text label that you have to update its parameters. So that becomes instruction basically tuning. So you give the instruction to the model as a data, but you update the model parameters. Right, so the model always, let's basically behave this way. I want this model to always behave in this certain basically ways. Now, that's the same definition. This is an example of instruction. Like we have two good examples on the paper. So here, the title of this instruction is that we want to write a question that involves common sense of understanding of the event duration. Then you provide a definition. So this is the template. What is the definition? Like what is in this task you want basically to be done? Then you also say that I want you to emphasize and caution. The written questions are not required to have a single correct answer. So you emphasize to the model, hey, you know, be cautious. I don't ask you to do this. Then things to avoid, you know, for some sort of like alignment. Hey, don't do this basically, for example. Then you provide two examples. Here's a positive example, here's a negative example. For positive and negative is not as one correct, one wrong. It's like a positive label, negative label. So here in the positive says that there's a sentence, Jack played basketball after school, after which he was very tired. And then the output basically says that, how long did Jack play basketball? So you expect the output be that, and the reason, so you see the model output is going to be this. So you give a question or giving a query, and the model basically asks this question, how long did Jack play basketball? So you want the model ask that question basically. And then the reason is that the question asks about the duration of an event, and you see that you need also a reasoning for it. Then negative example, the input is that he has spent 2 hours on his homework. And the model outputs, how long did he do his homework? And basically you do the reason, we do not want this question. Why? Because there was a part of the instruction that if the duration is in, or if the answer is in the question, it's wrong. So here, the answer of this is in the question. So you're basically instructing the model like, hey, you need to follow these steps and you need to generate this data. So you want the model to generate this positive, negative, basically you have, and you can use this, you know, as fine tuning. You know, it's okay, this is good, this is bad. Now, this is another example. So you define some tasks, you give a really good definition of what you mean. It's like you first start with that, and then you create series of positive and series of negative. And you always give a context, some input, the model gives you some output, and you want an explanation. It's like why this is a good answer, positive, what's this negative answers. So you basically create these templates of question, answers by, or basically query and questions and the reason for that by the model. If you are be able to convince the model that understand the context and ask the correct question, that means the model knows what you're talking about. So what you understand the topic, right? So it's kind of like a proper way of building a good data set for your model. And then what they did at the end, you basically do that supervised fine tuning because now you have this data set of positive negatives. So then it comes a technique called self-instruct. And so the idea in self-instructing here is that you want to do the same thing. You basically have series of LM or LLMs basically that they are going to help together build data, for this model. So I think the main paper basically they start with 175 seed tasks, one instruction per task and one instance per task. So it's like a 1-1. And then you have this task pool, and you pass it to a large model, and the model says that basically this large model job is to create an instruction for that. Okay, so it creates an instruction. Give me a code from famous person on this topic. That's the instruction. That goes to another model. That model basically, it's just some sort of like a classification. It gives it here answer yes, no here. The first one on top you see, so it's basically this is output first, the other one says input first. So here says instruction, find out given text is favor against abortion, because it's output first, so the model first predicts pro-abortion, and it gives the input. Okay, so output first. The next task here is that give me a code from a famous person. The model first gives the input, says that the importance of being honest, and the output is that honesty by this person. You see, like there's a difference between what one time it produces the output of the model first, then the input. One time it produces an input, then the output. So you bring all of this, and you have another model here that job is filtering to get rid of which questions are not good, which instruction wasn't built nicely. And this basically goes back to the task pool, and this loop continues. So this way you basically create data. You can create all this instructional data, and the models that you see, those LLM models that you see, they're basically self-instructing themselves. They create a question, goes through a series of steps, filters out, keeps the good one, goes back, the model updates and continue. So that becomes like the idea of self-instruct. All right, so that's it. That's that one. And then the next one, it comes that this came with GPT 3.5 especially. I think 3.5, 3 and 3.5. I think 3.5. In context learning and meta learning. Now, the idea of in context learning here is that you provide a couple of things like 5 plus 8 equal 13, 7 plus 2 equal 9, and so on. And then the model basically learns this in context. And it's I think it's GPT-3 was when this came out. It makes it much easier for teaching the model something. Now, so those are all of like ways that at least for now we talk. So in the previous class we talked about like some techniques for fine tuning, like LoRa, QLoRas, and stuff like that. And then we talked about like a prompting, and we talked about the concept of a RAG. And we are going to now focus on there's a concept of a scaling law, and because we want to understand how these models are getting better and better. Like what's going on that's with the models, and every iteration we are getting a better model. And so the idea was that in this scaling law that there's this paper by OpenAI, I think it's like a 2020, something like that, basically the main idea of the paper was that the more compute power, the more data, the more compute power, the more token and stuff like that you have, the better the model. So this was the result they basically published, that it's actually linear for the transformer models. The more compute, the more data, the more parameters, the error basically goes down linearly across all models, right? And this was like the idea for a couple of years everyone has, that the more data, larger the models, the better it gets, okay? So, and this was another example, like as we see, the larger it gets, basically, the error goes down. Then it came to, there's a paper called Chinchilla by Google. I think the name of the person is also Chinchilla. It's from Deep Brain, I think. And which year this came out? It's more recent, it's like I think 2 years, something like that. So Chinchilla paper came out by, and it basically rejected all those hypotheses that OpenAI had on 2020, that scaling law, the concept of the larger, more, is not actually accurate. So what they proved was that they built this model, is actually called Chinchilla. It has 70 billion in compared to all of these models. But there's one big caveat. It has 1.4 trillion tokens, training tokens. And it outperformed all of those models, much smaller. Basically what at Google basically they are saying here is that it's not about the more larger model, basically. It's about more efficient and better data, right? You can have a much smaller model with more data and a better training pipeline, optimization for how your model gets the data and stuff like that. And you outperform all of those. So now this idea of the scaling law went away. Now it's like a Chinchilla law of for the scaling. So that was up to a couple of months ago. Then DeepSeek came, right? And DeepSeek basically, it's still kind of following this idea of Chinchilla, because it's like, okay, it's a smaller model, but it also doesn't use that much token, smaller data, right? So it's kind of like it's rejected all of this. Some great extent it follows the Chinchilla, but the main advantage of DeepSeek approaches, or at least not advantage, is like a interesting that happening is that what they did is the way that they optimized that model. All of this model that we have, at least in the US, we have a really great set of GPUs that we run those. And one of the main challenges that these large models they have is when you train lots of models together, it's highly possible that certain nodes or GPUs fail as it goes, right? So the training is not that straightforward. DeepSeek has a much smaller amount of GPUs and less powerful GPUs, because it's banned, they don't ship those GPUs to China. But their training ends up become much cheaper and more efficient because they have less breakdown across this, like a training pipeline, right? So that also becomes another thing that, well, everything that up to this point we believed, is probably doesn't, it's not valid anymore. Now, there are a couple of things that also they were talk about. One of the ideas this says here is that the problem with these models is that we have this data, right? And all of this language, like a larger and larger models that we generate, the idea is that, well, if I have more compute, and this OpenAI still goes for that I have more compute, I'm going to make it better, right? One of the problems that it has been raised these days is that it's not about compute anymore, because we have lots of compute actually. It's about the data. Data has become like a blockage. Why? Because where does this data comes from? Web crawling, right? And there is a limitation to web crawling. So even you have more compute power, you still do web crawling And lots of this data are right now is like generated, internet is full of same data generated by basically models, right? So that becomes a challenge, and lots of companies focusing on maybe synthetic data generation for model improvement, because the web crawling is at this point is like a internet. It has lots of data, but lots of like a bad data overall. So that is right now a different challenge that have for improving the next generation of models, because the data is not as good. All right, any question on those? All right, so, all right, I think we talked about this in the previous class, but just quickly, these are like some insight from pre-training. Like if your model has pre-trained properly, it should understand in basically sentences like this. It should understand the grammar. It should understand like syntax, trivia, coreference, topic semantics, semantic or sentiment, and so on. If the model has learned those type of like the data, it should also understand those types of questions. Now, there are additional challenges in pre-training, well, one challenge is that memorization. These models basically crowdsource the internet, and there are lots of sensitive data that the model might memorize, and that becomes a big challenge. The other one is like a membership inference. Membership inference basically is the idea like if you could figure out a model was used over someone's data, for example, that's membership inference. Someone's is part of the certain data. And these are like some articles of like all these lawsuits going on with different companies for the problem with the data privacies and stuff like that. Okay, so this is just a follow-up on that scaling law. They did the study on other models instead of transformers, like for example, as we see here, LSTM and stuff like that. And transformer is actually the only one consistency goes down, and the other one after certain basic complexity start going up. So it wasn't linear anymore for those. For transformer is linear. For the more compute, basically it's showing that again, the error rate goes down, but for other types of model is actually not constant. It goes down up to a certain point, then start to increase. All right, now this is the just last picture. So this idea of like a transfer learning, you can pick model and transfer knowledge to use it for different tasks. For example, you want to use it for classification. You start with a starting token, a text, and you want to do extract something. You pass it to a transformer because it's a classification. You put at the end a linear layer for some, I don't know if it's like a binary, let's say binary classification. You can do something like entailment. Entailment again is that if this entails the previous sentence, so you have a premise and you put a hypothesis after, and the model need to predict yes or no. It's like entails. You could do similarities. You basically bring you have two texts, you put them once, text one with separators, then text two, the other one text two and text one, like the order is different. You pass both of them to a transformers model to become encoding, and you compare those. We see that if the contextual understanding with the reverse order of these two sentences is the same, they are similar. If they are not the same, that means that it changed the meaning of the sentence by changing swapping the basically order of the sentences. And then you can also do multiple choice, or there are different ways that you can do things like that. It depends on how you want to use this model. You pick a trained model and you just add a certain layers to the end, and you basically do for transfer learning. All right. Okay, I highly recommend you again to go watch this video if you haven't watched this GPT at the end. This by Blue, 3 blue, 1 brown. Definitely go watch it. So it just gives you a better understanding of these models. All right. Okay, let's take a short break. To start with reinforcement learning. How many of you have experience before? Have idea? 1, 2. All right. So just idea. Okay. So going to, before we start, so it's just the idea, the reason we want the reinforcement learning to go over it for the Gen AI course, because it's not a reinforcement learning course, is that certain tasks, depending on what you are doing in Gen AI, reinforcement learning becomes pretty critical, but only for certain tasks. And an example of that is just if you think about this idea of like an agentic, for example, AI, and you want the agent to do a decision, and then based on that, you want to be sure that optimally as it goes, that the agent needs to learn that, hey, this decision wasn't good before, I should basically take a better decision. Or if you think about the concept of like a chatbots, and you want this, when you do fine-tuning of these chatbots, you want to be sure that as it learns, as it goes, it becomes better and better at having a more coherent, more aligned, basically, generation. And that's why this the reinforcement learning becomes really popular. And one of the actually main reason OpenAI become OpenAI is actually the top researchers in OpenAI, they are reinforcement learning researchers. The idea that the algorithms that they came up, which we're going to talk about, is called PPO, and becomes one of the main ideas of like how this optimize for this models to make this actually learn in a proper way. So we're going to let's just start with the idea of like reinforcement learning. The idea of reinforcement learning is that it's just a way of to teach and code an agent or that to do something by taking and by interacting with the environment and getting a feedback. A simple scenario is that like if you are teaching your dog to, like you get a puppy and you want to teach the puppy to do something, you give a positive reward, negative reward for things that they do, and that becomes the mental model of like how to do positive. So the idea here is that in the classical machine learning, deep learning, you have a model, you have a data, the model basically learns from this data to map to that output, basically. In reinforcement learning, the idea here is that you don't have the data. You have an environment that you can get the data from, but you don't have a data. So you have an environment that you interact with, interact means that, for example, I go pick this, that's an action, I pick this is an action, and now previously the state of this marker was here. Now, if I took an action, the state of marker is in my hand. So the environment changes. Based on that, maybe I get a reward or a negative reward or positive. Maybe my goal is that to go and write on the board. So the sooner I go and less talk, maybe it's better for you. So the faster I pick this and get to the board, I get a better positive rewards. The more I talk, the slower I go, I get more negative rewards. Right? Like I'm falling asleep right now. Right? So that's the idea. There's an environment that you interact with. Based on the interaction, you get rewards. And based on the reward, basically, you update your behavior. The overall goal in this type of system is that we want to achieve the maximum reward, total reward. And we want to basically have the optimal policy, optimal decision-making policy. And another example is that imagine you develop a robot and this robot wants to learn to go from one corner of the room to the other corner. And you basically, the only thing that this robot knows is this physical movement that you coded and the movement, basically. It might not know actually how it take the movement. It just has a program of movement. You let this robot, maybe at first it crawls, maybe it just keep falling and stuff like that. So, and you define this basically mechanism that, hey, the longer it takes for you to go to the room, for every step, you get a negative reward. So your overall goal is that to get there with the less amount of steps, because that means that you would learn walking instead of crawling or basically ziggy-zaggy or stuff like that, right? So you let the robot to loop through this environment over and over again. And every time the reward is negative, it just because you have defined a goal, And the goal is that to minimize it. So it's finally tries over time learns that, okay, this is the optimal basically path, optimal way of walking. And also maybe here I need to step forward, that then going left and then right. So it's just a layman term of this. So it's actually, of course, there's more to it. It's just not just walking. So, so again, we have an environment you interact with. You have an agent. Agent is just could be your robot, your code. Or, again, the agent term is really vague these days. Agent takes an action. Agent could be that they pick the marker. Environment based on the action I give produce two things. One is that what is the next state of that environment? What is the reward of that action? The agent gets that as a feedback, basically, and then continues. This kind of like a loop of action, feedback, action, reward, and update, a state update, basically. So, is that clear so far? Now, we're going to start with something called Markov decision process, or basically MDP. So MDP is like it's going to be like one of the base definitions that we're going to work with in reinforcement learning. But it's a mathematical framework, okay, for modeling basically a decision-making process where the goal is to find optimal policy or finding a policy like for decision-making. So it's a mathematical framework that you want to some sort of like a decision-making to find some policy, like or some decision making in an environment where the basically the actions that you are taking, or basically it comes from either some sort of like a randomness or some sort of like a control, you know. So I might basically do something, and the outcome of what I'm doing, it could be totally random. That means that, or it could be predefined. If you do this, you get this. It's kind of like either some randomness in it, or it's kind of like a predefined. So it's a mathematical framework for defining such an environment. Okay. Now, the following terminology is going to constantly being repeated as we go. So it starts with state. Again, a state is that set of all possible scenarios or situation that the agent could be in. That's a state. Okay, that means that like a state could be I'm here is a state, here could be a state, and here state, you know, it's kind of that those are the states. All possible scenarios, situation that the agent or you could be in, that becomes a state. Then you have action, becomes set of all possible actions that you can take. That becomes the actions basically. Then you have rewards. It's kind of like some immediate, like some real number feedback that you are, for example, receiving. That's a reward. Then you have something called a reward model. Is more like a probabilistic. What's the chance of receiving this reward at time RT means the reward at time t, given I'm in a state t at the current state, and I'm doing this action. Like that's kind of like a reward model. So reward itself is just a reward. Okay, just reward that you receive. But you also could have a reward model that's kind of like looks at it like a probabilistic. What is the chance if I do this right now, I receive $5? Well, that's the reward model basically. Then we have transition model. Transition model is that it's kind of like if you think about it, probabilistic view of like moving from here to here. If I right now take, what's the chance if I take one step, I basically go to this location. What's the chance if I take the bus, I reach to work on time? That's the transition probability. It's like a probabilities of between the transiting between states. Okay, from one state to the other state, what is the probability of movement or transition? So that becomes the transition model. Okay. Then you have something called discount factors, and the idea of discount factor is that. So think about making money, right? So someone comes tells you that, hey, I give you this much right now, and come, for example, work for me, and I don't give you anything in the future, right? This is just a fixed money. And someone might tell you that, hey, I give you less money right now, but I give you, I don't know, some sort of like a shares that you get it over the years, right? So one of them is immediate reward. Like I give you this money right now, that's it. The other one is like a reward that you receive now and some indication of future reward that you have. Like it's like a discounted future. Because if you think about it, like I don't know, the 1 million that maybe you get right now, next year it isn't worth 1 million because of the fluctuation of it we have, right? So it's maybe worth less. So discounted factor basically means that the 1 million right now versus next year, it's not 1 million, it's discounted. You need to basically account for it. So we have this overall, basically we have this metric between 0 to 1. You choose how much that discount factor should be. Like this, you basically say that how much future rewards are important in compared to right now reward, right? How much investment is important compared to what you have at the moment. So that's the discount factor. Now, then it comes to this Markov property. We are still in Markov decision process, the definition of this framework. Now, Markov property basically is a property that says that the state that you are right now only depends on previous state, nothing before that. That's the idea of Markov property. Okay, so Markovian property, always like you say that whatever I'm in right now, it depends only at my previous state, not other states. So that we see also what it means, probability of being in a state given previous one is the same as probability of this state and whatever it was behind. So that means it doesn't depend on the rest. It only depends on ST. All right, those two are the same basically. So here, for example, here you have a sitting, a standing, foot forward, crash, shutdown, and hand raised. Basically it says that if you're in the sitting, a state of sitting, you have P, this is for the transition probability. You have like a 10%, this black one, 10% chance of going to shutdown. Right? This is for the robot. A robot that goes around and its robot could shut down, could crash, could be sitting, could be standing, foot forward, could hand raise and stuff like that, right? So shutdown is when the battery, for example, dies. Like imagine the Roomba, for example. So there is if you are sitting, there is a 10% chance you will shut down. There is a 60% chance after sitting you will stand. And then there is a 30% chance, for example, I think this is like for students actually. It's like you raise your hand. Shutdown is for those of you that fall asleep. So, and then every state has some transition probability. Some states, they have the loop also. It could go back to the same thing. The red that we see is a reward. You could, if you're sitting and you fall asleep, well, you didn't learn much in the class, so you get a -1 reward. If you, there's no positive reward apparently for standing. So there's only actually negative reward. So this is So this is a model that you only get negative and 0 reward. So you want to make it positive. Like you want it to make it less negative technically. So it doesn't give you a positive reward. It just gives you a negative rewards. So this becomes at every state, you only depends on previous one, either yourself or the previous one, nothing two after, two befores and stuff like that, right? Immediate basically transitions. So that's the idea of like a Markov property. Is that clear? All right, so now we're going to start with something here, observation space. There are two definitions that becomes important for you, terminologies like the state and observation. And it should be easy for you to remember. If you're looking at this like a chess game, this is everything. There's no hidden information. If you see this, you know everything, right? So that's a state. When you look at the information, there's no hidden data. Everything is in front of you. Observation, you don't know what's coming after Mario goes forward. That's only what you see is for the moment that you are in it. You're observing something, but it's only limited to the time step. So you hear the term observation versus state. A state is a full picture. Observation is just what you are seeing at the moment. Okay. Then you have something called action space. An action space is just, if you think about it, just a simple scenario. Like this is like if you do a 2D actions, this is the action space. Your action could come anywhere from here. Now it becomes 3D, then this is your action space, for example. And that's the idea of action space. Now there are two types of action space, discrete or continuous. Discrete means that the actions are straightforward, left, right, jump, down, or stuff like that. This, they are discrete. Continuous, like it could be anything for self-driving cars. So the actions are basically like infinite, for example. So that becomes continuous action space. So discrete versus continuous. Then you have something called policy. Okay, so policy is basically think about it like the brain behind the behind the decision making. So it's policy is basically the brain that maps the state to the action that you need to take. So you're like, I'm here. What action should I take? That decision making comes from a policy. Like your brain has this idea of like, when you're here, it's optimal to do this, right? Like if it's raining, it's optimal to action is to take an umbrella. So that you have that policy making basically model in your brain. So policy, the term policy, remember, is basically a model that maps the state to action. So that's policy, yes.
So how is it different from reward function, whatever we have?
So reward is just, so no, reward was,
It also-
no, reward function was probability of a reward given I do this and I do this. It's just what, if I'm in this state and I do this action, how much reward I will get? Policy, reward doesn't tell you that which one to take. It just said, if I'm here, I take this action, how much I get? What's the chance of this? Policy tells you that if you are in a state ST, you need to take action AT.
It tells us exactly.
It tells you what to do, basically. That's the idea of policy. Now, policy, there are two ways again, deterministic policy, stochastic policy. Deterministic policy is similar to that game, action space, up, down. Basically, it tells you that if you are here, take right, always take it. Like if the robot is walking, if there's a reach to the end with the wall, it says that turn right. You know, that's deterministic. It determined that by the state, what should you do? Then you have a stochastic policy, which is kind of like a probabilistic view now. It's like you might take this action, you might take this action. Right? We don't know yet which one is the proper action. So that becomes a stochastic view. Now, overall, yeah, there is a definition on bottom if you see. So basically that says that policy star equal, we have argmax, oh, I have it here, discounted value of rewards. And you have T from 0 to H. And you have P. Okay. So first, policy star. A star stands for optimal policy. So that basically says that the optimal policy comes from this argmax, which the argmax is over the policy. That means you optimaling for the policy, right? So what does the argmax tell you? That there is a summation T from 0 to H. This basically tells you that T at time 0, H is end of the trajectory, end of the episode. What's the episode? The robot starts from here. If you reach to the end, episode ends. So that's from there up to until the robots reach to the other wall. That's the trajectory. T from 0 to H. So that's why you don't know what's H, like end of the trajectory. Then you have this discounted, remember that discount factor? Expected reward, okay? So think about this. So here basically we say that if I am, so this term, let's look at for one trajectory. So, oh sorry, there's a T here. So T from 0 to H. Step one, like a first part of the time, this becomes basically alpha to the power of 0, expected value of reward at time 0, right? Plus, gamma to the power of 1, expected value of reward at time 1, plus so on, right? So that's total summation becomes, you know, the total reward that you could receive from end to end, right? At every timestamp, here the reward is expected value because you actually don't know what action you are taking. You know, expected over pi means that, so this second expected here is that, well, I don't know, like at every timestamp, you actually don't know what's the reward. We say that I could take right, I could go forward, I could go left, I could go back. 4 directions that I have, right? So the reward at this time becomes an average of these 4. So that's this expectation. Expected over all possible action I can take, and every action has a reward. For that time stamp becomes my average, basically like my weighted, for example, reward. That's the reward at this time stamp. Right? Now, if I'm in the next time stamp, what's the average reward? All of that together becomes the total reward that you could, on average, gain from here to here, right? And repeat it for different policies. Remember the policy, we're optimaling for that, right? For this policy. So policy is like, you repeat this process multiple times, and then you have these policies. Among those, you pick the one that gives you the total maximum, total reward that you're receiving, okay? That's good.
Yeah.
All right, we're going to break this down. Just the formula, we're going to break it down. But that's just an overall idea of like, you want to find an optimal policy. Then optimal policy is a policy that could give you the maximum total reward that you receive. Okay, and we're going to see how we're going to calculate that. Now, so first thing you're going to see also this term policy-based method. So we have we talk about it more, but we have also something called on policy, off policy. So, but policy-based method is kind of like a method that it's methods that they're focusing on with policies, like on policy methods. Now, there are 2 types of policy. Again, we say that they're deterministic, which is, as we say, just the brain says either go left, right, and that gives you an action. Then becomes basically the stochastic policy that well, the idea here is that, well, it's a probability. If I'm in this state, the action is not deterministic, it's like a probabilistic. What is the under this policy, given the state, the action comes from some probability. Like imagine there are 4 or 5 probabilities. Every action has a probability of occurrence, and a given time stamp, one of those might have it depending on the probability of the action. It's kind of like a probabilistic view. It's not deterministic, like always this happens, like a chance. So, that's again stochastic deterministic. Now let's look at one example. So let's say you try to, for your project, you try to use LLMs, and there are 2 states, A and B, basically. So state 1, a student got access to LLM and decides how to adapt it to their project. That's state 1. State 2, you decided of how you want to use the LLM, like your state has changed, like you have the knowledge and how you want to evaluate the performance. So there are 2 states. There are 2 actions for you to adaptation. You either fine tune or you do instruct tuning. So there are, again, 2 states that you can go through and then 2 actions that you can take. If you do fine tune, you know that you need to train on a small specific data set. If you do instruct tune, you write a detailed prompt and instruction and stuff like that to guide the model. So these are basically the actions and the information that you have for those actions. Now, you have this reward model that, well, if like you have this from somewhere, let's assume for now, that if you are in basically if you're state A or state B, like if you do a fine tuning as an action, you get 10 plus, you give yourself a 10 because your model works good, it's like a 10 plus. If you do fine tuning, but the data set was too small or some bias in the result that you get -5. If you do instruct tuning and it was enough, you get 8 plus. Then if you do instruct tuning, it wasn't efficient, you do -3. Okay, so that's the rewards. Then you have these transition probabilities. And in this scenario is straightforward. From A, you always go to B. Is that what it means? So transition from A to B is 100%. Transition from B to A is 0%. These are 0. That means you cannot go from B to A. But in both scenarios, you can go from A to B. You always can go from A to B 100%, but there is no B to A. Okay, there's no reverse. Now, so now the question here is, okay, I want to do something like that. Well, how could I? So we have this, you have defined this like a definition of your project or something, but you're like, well, how should I decide if the action that I take is good or bad? Right? Because I might think of like, okay, 10 plus is the largest action that you can take. Is it actually the best overall long-term policy? Or is it like a 10 plus right now, but end of the semester, because it was really difficult, I wasn't able to finish my project and so on, then the total expected reward went down. Immediate reward might be high, but the overall reward maybe is not high. So the question will be that, well, how could we evaluate this? How could we basically have some evaluation technique? So the first way of we need to go over is called value function, okay? And value function is an estimate of long-term reward from a given state. If I'm right now here, this state that I'm in it, how good is this state in a long run? That's the value function. So value function, once again, it tells you that how good is this state from all perspective. It's not about how good is this state if I go right. It's how good is this state overall. Why that's important? Imagine you want to take an action and you're like, I want to go there, but you're like, how good is there if I go there overall? You know, how good is this location if I go there? If I know it's not good, maybe the other one was good, maybe I go there. You know, it's kind of like, it gives you some overall idea of how good is a given state.
With the value function, if you're find the optimal value, are we looking at maximizing reward or are we looking at minimum number of transitions as well?
Okay, first, we're going to get there, but a great question. So it's asking that, are we just maximizing the reward or minimum? That's all depending on your like a definition of the problem. Right? It's what I put as an example of the exam, like students, those are like a simple scenario. All of these models, they have lots more definition of what is cost, what is you want to minimize, what you want to optimize. So it's not just one parameter that directly you want to optimize.
So how is the, let's say you are there and you took one step to go further to judge whether that step is good for the longer run, just for what you said, right? So how is it going to judge just before carrying out whole?
We're going to get there. Okay. There are like so many algorithms we're going to go over, and every one is of them try to solve that differently. Okay. All right. Okay, so the first technique that we want to basically find this value function from is called Bellman's equation. Okay, so it's going to be the first one. Is basically it becomes Bellman's equation, and we're going to first. Also comes back to what you just asked, talk about dynamic programming. Okay? So the idea of dynamic programming is that, well, if I'm trying to optimize something, I'm trying to solve a task, and the optimal answer to this task, dynamic programming says that, could be achieved by solving optimal solution to its subtasks. So if I break it down into a smaller subtask, and each one of those is optimal, the overall, I have the optimality. So that's the idea of dynamic programming, right? So instead of trying to solve one thing at one shot, break it down and solve each one of those optimal. And that becomes slowly goes towards what you say, individual steps, optimal individually. Now, so Bellman's equation starts with basically here. So as we go through the concepts, whenever you see V, it stands for a value function, okay? And V of and S is the state, and P is always the policy. So the value of this state under the current policy. Remember, policy is a decision-making brain. Right? Under this update that I have on my brain, how good is this state? If you don't update the brain, it's always the same policy, right? So you haven't done any updates. We haven't talked about that. So let's say right now, there's a policy that you have. How good is this state under this policy? So that comes back from an expectation, okay? So one of the things that you will see as we go forward is lots of expectations because, well, expected values, that's what I mean, is because, well, we don't know everything. We haven't seen everything. So you don't have a deterministic answer. So everything becomes expectations. So here, basically what we say is that the value of a state comes as an expectation with respect to policy, immediate reward, plus discounted future reward. So Bellman equation basically says that the value of a state, okay, comes from this expectation. We're going to talk about this expectation. Right now, if I do this action, what is the immediate reward that I receive? So I receive this much right away, immediate reward. Plus, I go to a next state because I took an action. How good is the next state? So, but I care about how good is the next state is kind of like a discounted in the future. Like I don't care right now. So the same thing. Oh, there's a policy. The value of the next state, given I am in the current state. Right? So that becomes the idea, like you take one step, you get an immediate reward, and you have a discounted future, basically reward or values that you know you can have. Now, so this expectation will break into this. These two are the same without the expectation. So let's understand what expectation says. When you say expectation under a policy again is a decision-making brain, right? The brain could tell you that took all possible actions, right? Could do everything, for example, if it's stochastic, not deterministic, it's like fixed. So if it's like, if you look at it from the stochastic perspective, or even deterministic, that means whatever is this value, you're doing a basically weighted average, expected value, right? What if I take this action, how much is that function? What if I took this action, how much was that function, and so on, and you basically weighted average. So it becomes an summation over the actions, all possible actions that I could take, right? So you have all possible actions that could take, and then you have all possible states that you could go. So there are two things. If I'm here under the policy, I could take so many actions. And this basically comes from something like this. If we think about all this is telling you that what action would have been possible from this brain, this pi is the brain, given you are in this state, right? And the summation basically tells you that all possible actions that the brain could tell you to take given you are in this state, okay? So now, ignore the summation and just think about one action. So the brain takes you to take one action. That one action, you don't know what it will lead to. It could lead to that I get here, it could get I got here, and so on. Because this environment, you don't know about it exactly. So that means the output of that action itself is summation of all possibilities that could happen. Not just one thing could happen. So if I am here and I took a certain action, just one action, I could go all possible states, for example. So it becomes, for that one action, a summation of all possible states that I could reach to. Okay. Every state has two things: immediate reward, discounted future reward. Every state. So that equation is the same. So every state basically gives you an immediate reward, RT, RS, S, and A, and discounted future reward. Okay. Now, there is a probability in front of it. What does that probability? The probability tells you that if you, what's this expectation? Right? What is the chance? It's like a probability that you get to that state. It's not like a deterministic. If I'm here and I take action A prime, 40% I go to state S, S1. 20% I go to S2. 30% I go to S1, and 20%, if I'm corrected, 10% I go to S4, right? So every one of those has a probability, right? So this basically becomes, if I remove this, let's just do it here. So let's say I took one action and that action was this A1. And basically this A1 basically was 20% possible technically times. And I have in every estate that I, there were 4 estates that I could go. Every estate was like a 20% times something plus 40% times something plus, I don't know, 30% times something plus 10% times something, right? And this times something is an immediate reward that you receive from taking that action to going to that estate and a discounted. So this becomes weighted average of all possible rewards you could get by taking one action. Now, well, there are so many actions you could take. So it becomes a summation over summation, you get expected value. So you have these probabilities of estates given S and given action, that action that comes from there, times immediate reward, plus discounted times like a value of estate S prime given you were in S and you take this action. Okay, so again becomes, but technically we don't have an action actually in the S in V, but becomes immediate reward plus the discounted. So let's actually remove this. We haven't. It's just value estate. We haven't talked about something else yet. So does this make sense? The idea again, if you think about it again, as we go forward, there's lots of expectation, is that things are not obvious. You don't know which action to take. The idea of value estate is that I want to know on average how good is this place that I'm in, or how good is the next place that I'm going. In order to understand it, you need to think about how, if I go here, anything could happen. So I couldn't, like you couldn't just look and say that, but we will see other algorithms that do that. I couldn't just look here and say that here is $100 worth it. Why? Because 100 was the maximum, the best case scenario. What about the worst case scenario, right? So in order to have how good is this estate, I need to look at every possibilities that this estate could happen. And as a basically weighted average, say that this is how good is this estate. That's how you can say that how good is an overall estate. Okay, so that's the Bellman's equation. Then you have Bellman optimality equation. Basically, you want to pick this. This is a value of an estate. Now the optimality equation is the other one. What's the maximum? What's the best case scenario that I could have for an estate? Right? So that comes from one thing. You could take all possible actions, correct? One of these actions gives you the best optimal. So Bellman optimality tells you that there is one action that gives you the maximum value, the best case scenario. So that becomes the action that gives you the maximum of this. So the first thing is that because you already know the action, so this part disappears. There is no probabilistic. You're already picking one action only. So it's not a weighted over all actions. It's just, I want the best one of those. So you don't have that. So you will have immediate reward. If I take this action, which I know is the best action, it gives me immediate reward. So there's an immediate reward for taking that action, which is the best action. Okay. Then there's a discounted feature. But for the discounted feature, you still need to think, I know what's the best action right now, but still that action could lead to so many things. So the second part is still probability of all possible states that I could go, given that action and state, times the optimal value of next state. So Bellman's optimality talks about two things here. The optimal value of the current state. It depends on the best action that I can take right now, which gives me the immediate reward, but also whatever state I go next in, the maximum value that the state has. optimality across all of them. The best case scenario for all states. So that means it's not like I'm here and I say that I know at this point, if I go straight, if I take one step forward, is the best steps. So when I go here in Bellman's optimality, you don't ask this question, what should I do now? Which state I should go now? You basically know that if I'm here and I go here, I already know this state has the maximum reward that I could achieve of 200. So everything is like optimal. So see, that's why you have this V star for the next state. In the one before, there's no star. Everything is just a random. You take action, you see what's going to happen on average and stuff like that. In Boltzmann optimality, you want the optimal answer. Yes.
So, I mean, we care about the immediate reward and the value of the state.
Mm-hmm.
So down the line, we might have a scenario where that path would lead to a very bad reward, maybe negative infinity. But in the beginning, we had like 100 rewards.
So it's like iterative.
But that would lead to a failure and then we'll have to go back.
Yeah. There's like so these types of models, they are not one-shot learning. There are lots of learning. So you might do a wrong pass and then you learn it and next time you don't take that action.
Yeah, but this function will not tell us if that pothole is going to come at down the line. It only looks at the next state, the next possible state that I want to take.
Yeah. So this one, so what we are seeing right now, you just look at one step ahead and just say that right.
Yes.
So we will go to the next types of model that we have so these are like a model based. So let's talk about it first. So these types of model that right now we go over, it's called model based. Model based is a types of RL that you know the environment, you know all possibilities that could happen, like a transition probabilities. They are types of models that they are model free. I don't know what's going to happen. In order to learn those models, you actually take a full action, series of times, right? And you keep collecting samples, and based on that, you learn what is possible, what should I take as an action. We will get to that. Right now, these are like a model based, and it's just you have defined this, and just one step ahead of that.
When you say learn, previously learn was changing the parameters, like the weights and stuff, but here learning changing what?
Policy. So think about this. What you do here is like you like agent is trying to do something that you define, that is end goal. The way that the agent can do it is by taking actions, right? Environment, there's an environment, you interact with the environment. Based on your action, you get a feedback. If you learn to have an optimal action, optimal decision making, you reach to a better answer. So you update that brain, the parameters of that brain.
Optimize the policy.
Yeah, we're going to get there. All right. So.
Sorry, I have a question about the mathematics here. So R of t plus 1 only depends on S and the action.
Yeah. So immediate reward, like if I am this state and I took this action, correct?
So the S prime doesn't affect the immediate action, immediate reward.
So immediate reward is for the current state and the current action, not S prime.
Okay.
Where it leads to, which becomes S prime, that comes from this transition probability, right?
Okay, so shouldn't it be R plus P times gamma times V?
R plus.
Because the probability of next step doesn't have anything to do with the immediate reward.
Possible. Let's see. Let's say, so let's go here. So let's say we take one step. We take one action, and this action could lead to all possible states that we go. This is the one before, that's right.
This one and the one before that, these are not the same.
This is the value function. This is the Boltzmann equation. That's the Boltzmann optimality equation. So here, basically, we say that every time I take an action, there's all possible scenarios could happen. Okay, based on that scenario, there is a reward that chance for that reward that I receive. Because one way of putting it is that imagine you're flying a kite, right? And the action is that you let the cable goes up, and there's an environment. So it's like there's a wind comes through based on what's the chance of wind. You get some reward, and based on you get some immediate reward that your kite goes up, but you get also discounted reward of being up there. But if the chance of wind is low, so you get less immediate reward because your kite doesn't fly at the moment. So current, like the chance that the state that you are going to still has some impact on what you could receive from the reward perspective. What you're saying that actually, I think we will see down the road, there are types of things, the types of states that what you get is just based on the action that you do right now, not where it leads to, not how the environment's interactive. But here's like an average like possibilities that could happen. Does that answer?
Yeah.
So, and so just a simple example here. You try to make a decision about a day planning, and then you're like, well, I have a morning choices, and I could go to the museum. Is a low cost, is informative. I could go to amusement park, high cost, lots of fun. Then you're like, I could go also in the afternoon. The museum, I still have more time and money for other activities. Amusement park, I have less time for money and other activities because I just also did that in the afternoon. And the decision making is that, well, I want to balance between my immediate and future overall, like a reward that I receive for planning. So if you go to museum, you get 40 points. If you go to amusement park, you get 50 points, like from the thrills and activity. Joy. Now, it's a really long walk this way. I need to optimize that. So now if you go to future rewards, so museum has extra time and money, could lead to 30 more future rewards. And amusement park has fewer resources and could maybe give you 10 more future rewards. And you want to just plan based on that. And so the idea becomes that immediate reward plus discounted future reward. So for museum is that 40 plus 0.9 times 30. And amusement park is that 50 immediate plus 0.9 times 10. So total becomes 67 versus like kind of like you'd look at current, like immediate reward and what I could get in the futures. And that factor 0.9 is that you decide how much you care about features, how much you care about the current time step. So now, how we could actually solve for this, there are two methods that we can find this value functions. Basically solve for this like Bellman's equations. And then one of them is called value iteration. The other one is called policy iteration. Okay, so there are the two techniques that we're going to talk about. The first one is value iteration. So value iteration basically is that you want to find the best value for a given state. So you start with, let's say I have like 4 states that I could go, and I would basically create this, I don't know, tape or array maybe. That's a way of saying it. I create this array of value of state 0, value of state 1, and value of state 4, and all of them I assign as 0. At first, I don't know anything about it. There's 0 values. Then you repeat this until convergence, okay? So what's the repetitions basically? Well, I take an action as in a state, I take an action and I try to update it. So if let's do one. We do one quick example. So value at time at S0, value of state 0. At first, I put all of them 0 randomly, but I want to find the optimal value of state 0. And here, basically, we wanted to pick an action that gives you the maximum. Okay. So the first thing here is that, well, we don't have anything. So I could basically take one action, and that action gives me I took action A, and it gives me a reward of 10 plus a discounted, it takes me to the next state, S1. But S1 is also, I haven't gone there before, so the value of S1 is also 0, right? So it becomes this like a gamma times value of S1, which is 0. So value of taking this action in this state give me a 10, right? So that's my first iteration. Now I updated the value. If I am in this state and I took this action, I get a 10, right? So you keep repeating these experiments to get some sense of like if this state and you keep getting actions, how much value you have. But before you repeat this, so right now from S0, you went to S1, correct? So then you basically calculate what is the value of S1 becomes you take some action, random action, some immediate reward plus discounted times whatever state you go, value of that state, and you get the value. You repeat this until you reach to the end of the trajectory, like done. So that's one experiment, right? So then I repeat the experiment again. So you repeat this experiment a series of times, and then if you want to understand what's the optimal value for a state, becomes this considering taking the best action. Right? So because you have some knowledge, if you started from all zeros, we repeat it, all the passes that possible was possible. One of them is the best one, the one that gives you the maximum reward. So that becomes the optimal action, and this becomes the optimal value for that state. So this we call value iteration. You iterate over the values, just fix the value, like find the optimal value. Then the next one we have is called policy iteration. And policy iteration, it's kind of like a two states. Value iteration, you just repeat to get the optimal value for a state. In policy iteration, you have two steps: policy evaluation, policy improvement. And again, policy is the brain, the decision making. So you start here on this graph, you see a starting point, and you like at first you have everything maybe 0, and you do like a policy evaluation. What's the value of this state if under this policy I take an action? Okay, so action. See, this says policy action. That means is stochastic. It could be any action, for example. So if I take this action, I get immediate reward of this, plus I go to the next state, all possible next state, like a weighted sum, discounted weighted sum of possible next states and their value. That because my total value for this state, if I take this action plus the discounted future possibilities. Now that will take me here. Okay. Now I have that knowledge. So you got one knowledge, you do policy iteration, so improvement. You go say that, I made this decision before, well, maybe I need to update my decision making, and I'm going to, moving forward, take the decision that gives me the maximum of that. So then previously your policy was here, now your policy comes here, right? Then you take another updates on the first one. Now you have an updated decision making. You take another pass. You go here. Based on the pass and what you saw and which action was better, you update your decision making. Now you have an updated decision making model again, and you repeat that. So the idea here is that you keep back and forthing, and you will get to optimal scenario that now you have both updated like optimal value function. Wait, let me see. Oh, you don't see that. Sorry. On the screen behind you, I see this TV standby, but it apparently doesn't show it here. I was like, yes.
So I couldn't really exactly follow along. Could you repeat a bit?
Sure. So there is you start in a learning. So you have a policy. You have this brain that given a state, it basically tells you take an action. Okay. So, and you want to say that, okay, I am here, I'm in state S. What is the value of this state S? Okay. So you said if you're in a state S, you will get an immediate reward given you are in this state And under this policy, you take an action.
Okay.
Okay, a reward that you take under this policy. Then after that, well, when you take action, you always go to some other estates. We don't know which estates you go. So what we say is that it's going to be a summation over all possible estates that you can go. And there is a transition probability. Transition probability will say that if you are here, you take an action, there's a 20% chance you go here, a 40% chance. So there's a transition probability. For every estate that you could go, there is also itself has a value. How much that estate is good? How good is that estate? Let's put that way, right? So value of that estate, given I'm coming from our estate, we don't actually, it's just value of that estate. So this tells you that how good is the current estate that you are, and if you basically, how good is this estate that you are, value of estate is, okay? So you have this knowledge, then you had this brain, you're like, okay, well, I took some action, I saw something, I'm going to change my behavior. So next time I learn something, I'm not going to be able to take this action. So how do you do that? The overall goal of the policy is to give you the maximum values, right? So you basically say that my optimal policy is going to be across these actions possible that I could take, I'm going to pick the one that gives me the maximum argmax of this value. Immediate reward plus this discounted. There's two things here that you need to notice. In the one above, in value, this is a policy over S, this term, which says, if I'm this estate, under the policy, there is action that I take. I don't know what action. In the second one, it's action. There's no policy. Because it's not stochastic anymore. You pick the best action. Here, it's stochastic. It could be any action. Here is the best action. So see, that's the difference. And there's an argmax behind it. So you do that and you find the optimal policy at this time stamp, right? So now I have a better model, decision-making model. And I'm like, well, I'm great. I'm going to bet. And I do, and I'm losing something. And I'm like, oh, I did bad. I change my mind again on like how I need next time to bet. And I try it. And I say, every time you do back and forth, just do policy iteration. So you make a decision, you see what happened, based on that you update your policy and continue. And if you repeat this enough, then you get to a point that you have the optimal value for every estate and optimal decision making. Is that clear?
So for the policy improvement, do we calculate that particular expression value for every possible action that we can take in that particular state? That's what you're
So you do argmax, yes. So you need to have.
We do argmax and then we note that action as the current action.
Yes, so you know if, so when you do argmax, that means you have done that action, you know what's the value of that action, right?
So which one goes first, Professor? Policy evaluation or the policy improvement?
Policy evaluation. So I mean, at first, if you think, if I start randomly, I might put everything 0. So if you pick argmax, it's always stays 0, right? So you need to take a step, see something happens, learn something, and based on that learning, update your mental model. Right?
So basically, we're asking two questions. First one is, which is the best policy value? And then we ask, which action would give me the best policy value?
That's right.
And could you show me any examples of the reward function and the probability function so that we can see how they look like at least? Any reward functions, like we are seeing an expression right now, right?
So this is a reward function.
Example of that function, any function that is being used or?
I mean, reward function could be a function that says that if you are, let me like a real life example, let's say,
Gaussian or something like that. For distribution, we have a Gaussian function, right? So for reward function, is there any example, the standard example you could use? Something like that?
That's not connected to Gaussian, so let's just make an example. So reward function says that, let's say I'm a robot, like a Roomba, cleaning Roomba, right? And the Roomba is that if I continue cleaning, and I'm like 10% battery, if I'm continue cleaning instead of going to the charging deck, I get, for cleaning, I'm getting 80 points positive because I'm keep cleaning, right? So that's a reward function. Taking this action, keep cleaning, you get 80 points, immediate reward. The transition basically says that if you did this immediate reward and you're cleaning, you keep going to clean the next corner of the house, right? So those are like a reward that you get and you start the cleaning. However, in a longer run, what happens, if you think about it from the action policy updates, you went, all of a sudden the battery died. So you learn, when you next time you want to update, you say that, well, battery died midway. What happened? My battery was less than 10%. I take this action instead of going to a dark charging deck. I basically went this direction, right? So I'll update my action based on what I saw before.
Okay, so there lies my question. So those 80 points you are mentioning. So do we physically hard code that into the system, or does it derive it from any function?
Okay, you can do both. You can formulate it yourself. You can basically hard code it. And even on the transition probabilities, like if you think about it, actually, as we go forward, we'll see that these models are more difficult because you don't know the transition probabilities. The other algorithms will come up. These are like the earliest version of the reinforcement learning that you see. But the reward model, for example, I actually worked on one of these like a thermostat changers. And the idea is that we made a decision that, okay, I'm going to increase the temperature based on some metadata that we have, and you give a reward. We used to give a reward if the user doesn't change the temperature, comes back and reduce it, and how long does it take before the user comes back and reduces, like a time based. So you have this function that formulates. It's a formula that based on those information gives you a reward. If user comes and you go to 70, user comes, brings down 68, that's a really large negative reward, basically, that you receive.
User input was required there. That means we are wrong.
Yeah, I mean,
update was wrong.
So your reward could be just reward, defined reward. If you are here, you go here. That's a defined reward. Or your reward could be probabilistic. It's like if I do something, there's a chance that I earn this much. It's like a probabilistic reward. It's like a function that gives you that. It's not deterministic. And that function could be defined. You end up as a researcher, you define it yourself. It's not something that is given to you. Like the thing about the reinforcement learning is that it's unknown environment. You go to learn it. So most of the things are not given. Okay, and the more complex it gets, the harder the environment. It's like harder to learn.
Professor, just one minute on that. On that formula that you had, is there scope of improvement, or I think we're double calculating. I might be wrong, but so we are also, when we are doing policy improvement, we already have that partial sum somewhere, right?
Yeah. You have those. You are not double calculating. You have this.
Yeah.
You just do argmax over them.
Yeah, you do the argmax and do the summation and everything, right? You get one of those values is what we are calculating for the evaluation also, right?
So the one on top, you calculate.
Yeah.
The one below, you just do argmax over the one above, possibilities.
Yeah, okay. So you don't have to, okay.
You don't need to recalculate. You basically, you keep track of those. All right.
Sorry, so I understand what is the immediate reward of an action. Then we know the action. But in the first equation, we have the immediate reward of the policy. Is it the summation of all actions that we can do under this policy?
So, yeah, so great question. So what your friend is asking is that this policy could give so many actions. So you can have this as a weighted sum like what we saw before. You could have a function that is a function, you just say that there are a series of actions that they take, but here in the case of value iteration, or basically the policy evaluation, this policy could give series of actions, weighted like this, it could go left, could go right. Each one of those gives you a state, and that state basically provides you others. So yes, that becomes a summation over possible actions. That's what I said. So the first one is a policy, is not deterministic action. The second one is just, all of this, you take an action basically. So that's again, policy iteration, value iteration. Now, so one of the things about this too is that there are lots of iteration could happen. one way to optimize it is is a technique, like a version of this modified policy iteration, is that instead of doing so many samples, you only take k iteration, basically. It's just kind of like you repeat it only for k times. So same formula, but it's kind of like you just take, you do a basically partial evaluation. You don't do it through the end to evaluate it. You just do k iteration, evaluate it based on k, and then you continue to next steps. So instead of doing through all of it and back and forth, because it becomes a bit slower, you just do sampling k iterations. Now, the main challenge is all of this, which so far is the dynamic programming, is that, well, these are model-based and this require that transition probabilities. All the formulas that you saw, they require this change, this transition probabilities. And that means that you need to know at every step, if I'm here, I do this, where I will land. And if you're in a learning environment where you don't know those, it's really hard to have those knowledge. So that's why, again, dynamic programming is like, despite the fact they're really, if you know the environment, they work really good. And in most of the cases that we don't know the environment, they are not applicable. Okay, so that basically brings us to model-free types of models. A set of models or techniques that, what if I don't know about this environment? What if I don't have a model of this environment? It's model-free. How could I basically interact with this environment? So the first one is I think we're going to talk about, so again, the goal is still to understand that value function. So as we go through all these techniques, the goal actually remains really constant. So we want to know how good is a state always. This state next to how good is the state. We also want to know what's the best action should I take. We still have the same goal. Just the environment, types of modeling is going to change. So the next one, which is the model free, we still want to find a VP, like a value function for a state. But I don't know what will happen. So I don't have that transition probability. So I cannot use that. So instead, we use something called Monte Carlo methods. Monte Carlo methods, it's basically the idea of the Monte Carlo is that, well, you sample. You use sample instead of the reality. So we use Monte Carlo a lot. I think in this class, we will see more often of it. But think about it as like a simple scenario is that there's a distribution and you sample data from it every time. And that means I can sample from this data, but I don't know the distribution of this data. So if you tell me what is the probability of this data point, I can't tell you. I know this data comes from this distribution, but I don't have this distribution. I cannot answer you that. Similar to this transition probability, there's an environment, there's a probability, but I don't know it. So instead of that, Monte Carlo says that, well, sample 100 points from here. Okay, you have this 100-point sample. So let's put it in a bucket. Okay, it doesn't matter if it comes from here or not. Now, this 100 points are uniform distribution. Every sample that is in this bucket, you can sample from it again with the uniform probability. Correct? Because it was from here, but now it's uniform in a bucket. So now, if I'm trying to calculate some expected value, instead of doing an expected value over an unknown distribution, I do expected value over a known distribution. And every sample so expected value of a function is always basically p of x, f of x, right? Probability of that point passed to the function, right, on average. So you always need this probability, right? So if I don't know the distribution, I don't have that probability, so I cannot answer that. But if I do Monte Carlo, every one of these has the same probability, correct? So every one of this probability is the same across all. So Monte Carlo, basically, as you see here, it says, you sample an S data point, N stands for number for that S state, average those all. They all have same probability. You basically multiplying it. Think about it. Let's say you have 10 sample, so every sample has 0.1 times the value, correct? So this is the same as if you remove, or the same as 0.1 times summation of f of x. Right? So that's why in Monte Carlo, you always see there is a 1 over the size of the sample behind the function. So instead of dealing with an unknown distribution, unknown probability, I sample, now it's known, I have it. And every sample is uniform, same probability. So here we couldn't find these transition probabilities because we don't have it. So we sample, and we've talked about this. We sample and we calculate this over that sample that we have. Now, what is this term here? This is the same thing that we saw before, value state, like a value function, right? So value function says that expected value over a policy, same thing that we saw before. Summation over discounted rewards, okay? So that's just writing the same thing in a recursive function. Value function is, so ignore the expected part, just look at this, what's in the summation. So the summation over this, the power of t, what do we have? RT, right? T from 0 to, what do we have? Nothing, right? Let's say t is from 0 to p. So this becomes gamma to the power of 0, R0, immediate reward, plus gamma to the power of 1, R1, and so on, right? If you think about it, if you pick the same thing that you have, expand it in a recursive way, immediate reward plus discounted next reward plus. This exactly becomes the same thing. So here, the value function is coming from this. We don't have that transition probability anymore because again, this is model free. In model free, you don't have this part. Okay, there's no transition probability. Everything basically comes from this immediate reward plus discounted reward. So you can write the value function as this formula. Expected value over all possibilities that the brain can tell you. For every possibility, there is a summation of immediate plus all sort of discounted rewards through the end. Okay. So how do we calculate this? In Monte Carlo, we said that, well, this expected value also, I don't want to deal with it. So what do? Well, I do sample. So I sample for n times, and instead of having because expected value sometimes is really vague, like what do we mean, how many times you should sample and stuff like that. Well, I just pick 10 samples and I do average over 10 possibilities. That becomes the Monte Carlo basically approach. Yeah.
We sample for every value, every step.
So this is sampling. So there is a policy. So for a given policy, you sample basically 10 trajectory. So what you see, there are two summation. The inner summation, this one, is I actually should have said that before. Sorry. So in Monte Carlo, you start here, you go all the way to the end. Monte Carlo is a full basically trajectory. So basically, you go all the way to the end. Then you stop. That one iteration, one epoch is done when you go from here to here. That's why here you see discounted reward from now through the end. Monte Carlo is a sampling because if you think about it, it's model free. I don't know about the environment. How do you learn? Go explore. That's the reality. You let it go to explore. You let the agent go from your goal. You're here. Your goal was to go there. When you got there, restart. You let the model. Doesn't matter how long it takes. Just go do it. And you do this sampling by letting the model. Basic agent does the full process, and this is the full process. The summation over t. T here means like this is your trajectory. Could be anything, or could take any. Every step you have a reward. From the current step, you have a current immediate reward plus discounted all the way. So for one sample in Monte Carlo, you get this. If you do 10 samples, you get summation over 10 divided by 10, because remember that was 0.1 times. So that becomes the Monte Carlo estimation of a value of a state under a certain policy, under certain as decision making. Does that make sense? Yes.
So like, what are the chances of this method finding an optimal solution?
I mean, Monte Carlo overall actually, it's a technique that it requires more iteration, but it actually has three good properties. I think we talked about this Monte Carlo before, but there had three. Maybe it's coming forward. It has three properties. One of them is a variance reduction, unbiasedness, and it's actually the convergence. So the Monte Carlo will, if you keep sampling, it will converge. Okay. If you keep sampling, the Monte Carlo is unbiased. I think we did it in the class. If you do expectation over the expectation of the Monte Carlo, it gives you the same function. That means it's unbiased. Variance reduction means that if you keep sampling, the variance of the estimation slowly goes down and down the more sample you have. So that's why it's a technique that as we go, especially to image concept of the next week, the week after, and so on. You see that Monte Carlo, almost every algorithm, we kind of do some sort of sampling because it works. I need to go, but go ahead.
Oh, yeah. So my question is like, I want to discuss the implication of removing that probability edge.
Let's discuss that later. All right. Any discussion? Let's keep for after the class, so I can just go through over this.
Yeah.
We already like that so far. Anyway, so that becomes a value function. So remember, this is a full trajectory steps, Monte Carlo model free. You don't know the environment, just explore it. So, and here this is the same thing we just talked about. What we do, basically, or what you see, instead of writing this summation over immediate and discounted reward through the end, you will see this GK. Okay, that's like a total reward for one sample, one full exploration, basically. Okay, so that's the same thing. We just, instead of writing the double, we just put GK. Okay, so that's the same thing. Full one sample end-to-end reward collected, immediate and discounted. So in the example here, you see, if you're at D, state D at time T, here, and you define two end to this exploration. If you go all the way to G, you get +1. If you go all the way to A, you get -1. And you start always from D. One time you sample and ends up D, E, D, E, F, G. Like a robot, for example, moves and you get a +1. Next time you go D, C, B, C, B, A, and you get -1. That's two Monte Carlo samples, full trajectory, basically. Here the reward was just at the end, not immediate and discounted.
Sample can have multiple trajectories.
Sample what?
A sample can have multiple trajectories.
One sample is a full trajectory. One Monte Carlo sample is from the start until the end of the trajectory.
And this +1, is it the reward for reaching G, or is it the reward
The
for
total reward. Here in this example, I didn't have a discount. It's just a total. If you go here, you get +1. If you go there, you get -1.
But is it only for following this particular path, or is it?
No, anytime you reach here, you get +1. If you don't reach here, you haven't done. You need to continue.
Continue, okay.
Whenever you get to both ends, you are done, basically.
So at the end, we are trying to get the robot in a shortest way possible, either to G or A. So hopefully,
Could be, depending on what's your end goal. Like you want the shortest pass, or you don't care. You want overall. Now we can look at the we can approximate basically this value function. So instead of trying to find it in one go, you can use a basic approximations or some incremental learning. Basically, the idea here is that this is the value function. Okay? This is what equation we just saw. Average, because it's a Monte Carlo sampling, over the total reward for each sample. So you can expand this technically. So this is, you do n samples, n full trajectories, correct? So what you see here, we expanded how we pick the last, like one of those. So this is 1, and put the ns minus 1 together. Okay, this is n summation. Pick one of the ends and put n minus 1 summation here. Then this one will mean this. How? So if you think about the formula for Vs, the formula for Vp, what do we say, Ns, that's basically says it's N over S summation of G, K, and S, correct? So in the first line here, what do we have? Summation K from 1 to Ns minus 1, right? So summation GK Ns minus 1, right? Do you agree this is the same as, oh, do you agree first with this? Ns minus 1, Vp Ns minus 1, correct? So now if you move this to the other side, this equal Ns minus 1 times that equal to this. It's just a recursive function, you just move the elements. So that's how this came. From here we got to this. And then you just move them around because they both have Ns in common. So you move this around and this becomes 1 over Ns Gn. Then you have this times that, and then you have this times that. So this is a step size or like a learning rate basically, 1 over Ns. Ns is the number of time you basically visited the sample, like the number of sample for that state. That's the learning rate. So this basically looks like this now. The state value could be approximated using this equation. And this equation is really similar to what you saw probably in gradient descent. My previous value, my previous estimate, plus a learning rate times how much I received, right? How much I actually earned, minus how much I believed I actually going to learn. The error times learning rate plus my previous step becomes my updated value. So at every step, you can incrementally update your belief about the value function by like, I believe this state worth 10, for example, 10 points. Then I basically do a full trajectory. So I'm right now here, I'm saying that I believe this is 10. Then I'm like, okay, let me do a pass around. I go do a full trajectory and I earn the reward. Okay, I do a full trajectory, I gained like, I don't know, like a 8 reward. I believed it was worth 10. So the error, the inner bracket is learning rate times 8 minus 10. 10 was my previous belief plus this. That becomes my updated belief. And you keep, so that means you don't need to wait for 10 Monte Carlo samples in order to do all of them to update the value state. You can do incrementally, one at a time. Every time you have a belief, you do a full trajectory, update your belief, continue, and continue. It's much better, much faster to basically update, right? Yes.
That summation would just be an approximate, right?
The
Ns minus 1 into value function equals summation.
Yes, so there's approximation, sorry, in front of it on top. Yeah, sorry, that's not equation, that's approximation.
So because they wouldn't have same values. That's the only reason.
Yeah, so I mean, it's approximation overall.
Value functions can change, so it's just approximate.
Yeah, so so the same equation, basically, that's like approximation also.
Thank you.
All right, so that's for value function and incremental update, basically using Monte Carlo. Now, just a quick recap between Monte Carlo and dynamic programming. Monte Carlo, it directly learns from full episode sampling. It averaged the observed rewards based on these samples. It only gets the reward at the end of the trajectory, not midway. It cannot do any bootstrapping. Bootstrapping means that I do one step at a time and update. It's suitable for environments that you don't know, is unknown. Dynamic programming is model-based. That means it requires to know the transition probabilities. If I do this, 20% I will go here, 40% I go there. It uses the Bellman equations for updates. It's incremental basic updates. It uses basically that, is bootstrapping because it's just I'm going here, this is the value I update, and I go here and updates. And it's suitable for the scenarios that the model is known, right? So that becomes a dynamic program. Now, so the challenges of Monte Carlo, well, sample efficiency. You pick a sample, how good is this sample? It could cause, downstream issues. Computational efficiency, because you need to sample a lot. As I say, you need lots of sample actually to end up with a good results. The idea of bootstrapping capabilities issues high variance. If you, by default, you have high variance, but if you keep sampling, it's basically you reduce that variances, but again, it requires lots of sampling. Now, so next step here is that how could we basically do this? How could we update this value function without waiting to the end of the episode? So Monte Carlo, you do one full trajectory. The approach is great, but you need to go through the end. Now the question is, could we do the same thing, but don't go to the end in order to update? And that comes to the next types of algorithm, temporal difference, TD learning. Okay, and temporal difference, same idea of Monte Carlo, but well, you don't need to go through the end of the trajectory. So if you are on top and you want to, in Monte Carlo, the full trajectory means that you go all the way to the end. In TD learning, well, you just go one state, update, and you use that knowledge for the next steps. So you don't go through the end, okay? So now, basically the idea of TD learning is that, well, you take a step, you observe the reward, you update the stated values with this bootstrapping, and it basically gives you one single return. And we're just going to break it down. So now, the main difference basically comes, the algorithm is kind of same idea. Previous beliefs plus learning rate minus that update, okay? However, that update part in TD learning versus the Monte Carlo, in Monte Carlo was, the update would come from, I started here, I went to the end and I collected this much. I previously believed 10, 8 minus 10, that's an error. In TD learning, I don't need to go through the end to collect all the rewards. I just do maybe one step and I project like a bootstrap to see how much will be total. So it has this term, it's kind of like a look ahead, which is immediate reward plus discounted future rewards. Same idea, but it's like basically you use what you saw as part of the Bellman equation, that the immediate plus discounted minus the previous belief that you have. So this part, instead of in Monte Carlo, it was a GT minus V. Here, the GT doesn't exist because GT was a full return. Instead, you have immediate plus discounted future knowledge. You have this from previous beliefs. At first, you don't have, at first, this all could be zeros. So it becomes immediate reward plus zeros. Next step, updated, and so on and so on. Now, in a colorful way of showing it, as reward state value function equals the previous belief plus learning rate times immediate reward plus discounted minus this. Now, this part, you hear the term TD error and TD target, two things. So TD target is that reward concept, immediate reward plus discounted future. That's the target. Why target? Because if you think about it, I was believing that if I'm here, my value is 10. Now I will say that, well, let me see if it's 10. The target in my head is 10. So I wish whatever I do, give me a 10, right? So I take one step, then I bootstrap, and I collect the total, and that becomes the TD target, right? So that target minus my previous belief, that becomes the TD error. So TD target minus the previous belief becomes TD error. So again, you will keep hearing these two terms, TD target, TD error, but that's the idea of temporal difference learning. It's like a temporal difference, right? One step, bootstrap, basically estimation minus the previous estimation, that gives you the temporal basically difference.
So basically, we are dividing that whole stretch into mini parts and we are.
Bootstrapping, that's correct.
Yep.
Now, in TD learning, actually, we're going to here talk about that learning rate that you pick. It's actually need to be appropriated in order to converge. Here, what you see, this basically all says that even in machine learning, deep learning, when you want to have a learning rate that is adjustable or changes over time, you always write constraints like this. Means that learning rate, summation of learning rate should be infinite. That means learning rate overall should be large enough. Summation of learning rate to the power of 2 should be less than infinite, means that it shouldn't be too large also. That's mathematically basically what it means. It's like a constraints we put on adjustable basic parameters. So you want it to be overall across time large enough, but you don't want it to be too large also. So that's what it basically says. But here, an easy way for selecting the learning rate is just put the learning rate 1 over number of time you visited the state. So at first, the learning rate is always 1 because you haven't visited the state. When you start visiting the states, you keep tracking of how many times I have seen these states before, and that becomes the learning rate per state. So every state basically has a different learning rate depending on basically you want that update for that state. So this is basically the TD evaluation algorithm. This is how it works. At first, set all the states to 0. The value for every state 0. You do a for loop. Basically, you let it to run. You take one action, execute a P. I'm in this state. I'm taking an action. That's going to give me a one action. I don't know what action is, right? So that policy gives me an action. Based on that action, there's an outcome. I will reach to some state, which I don't know, and I get a reward. So I'm going to observe that, and basically observe means that to keep track of it. I know how much I earned by taking this action at this state, and I know where I landed. Then I update that frequency count for the state, because that becomes the learning rate, right? So I count. I was here once now. Previously was 0, now I have here 1. Then learning rate becomes 1 over that. You want to update. The update becomes my previous estimate for the state, which is first is 0. 0 plus learning rate, which becomes 1 over 1 times, because at first you only saw it one time, times immediate whatever reward you got, plus whatever is this gamma discounted times value of the next state. At first is 0, so just R, minus value of the current state, 0. So this total, even without knowing a number, at first is 0 plus 1 times R plus 0 minus 0. So it's R at the step 1, right? Because all of this is 0. So for value of a state 0, a state S, it's R. Now I have some information. Taking that action took me to a next state. Now I repeat the same thing for that state. At first it's kind of similar, everything is 0. So first couple of iterations is like a straightforward. Then you finish, then you come back, repeat, and the next time you start having updates, you have values and so on. You just let this loop until you get basically to convergence. You get to the point you're like, okay, the value of the function doesn't change. I think I have a good estimate of how good is this state. Does that make sense? All right, so, actually, this is a, let me see. Well, do you want me to solve an example, or do you think you can solve it yourself?
We want you to solve it next week.
we are behind. I need to solve this, or I need to go to the next algorithm. You guys can solve it yourself based on this. It's literally like there's 2 states, A and B. I think you should be able to solve this. All right, I'll put that as a homework. All right, it's okay. So we're going to go to end of this, and we will finish. Now the next thing comes is called a state value function. Okay, sorry, a state action function. Now, up to this point, we only estimated how good is a state, right? Just how good is the state. The next thing here is that, well, how good is this state if I take this action? You see, how good is the state considering this action? Right?
Before taking action or after taking the action? Like you ask the question in the before step.
If I take this action, like a
Previous state.
present, right?
Okay, yeah,
If I
yeah.
take this action, how good is this?
Good is
Is it
that?
on?
Got it.
So previously, we just were looking at states. There's no action constant. Here, it becomes a state and action. This becomes a mapping. So same idea. Like a previous belief at first is everything is zero. Same formula. Instead of anytime it was a V, you just put Q. So Q becomes basically like a expected return after I take one action in a state. If I'm here, if I go forward, what do I think forward gives me? That's a stated, like the total reward for taking this action. Previously, I was just saying like this. If I'm here, what I will achieve, how good is this? Now you ask the question, if I'm here and I take an action and I take a left, how good is that? If I'm here and I go right, how good is that? So it's like there's an action concept in this.
Is that not same as what we studied in Bellman, like the immediate reward plus the?
No, Bellman was saying that like you only care about the state. The action was giving you different direction to go.
But the action was given, right? Given action.
No, so the Bellman, we say that how are we going to back? It tells you that how good is the state given all possible action.
Yes.
Here you say that so the value that you get as Bellman is average of all actions. Here you say that how good is this state with this action? Condition, like with this action.
No transition matrix, nothing,
No.
just.
Action and states are together here.
Have the action as another constraint, isn't it?
It's conditioned, they are together. It's like a joint here. Like, so a state and action are together. So basically, you have a state and you have action, and you have this table, for example, of how good is that in being a state and taking actions. And based on that, you try to understand that you're still doing the same thing, because we will see the connection from this, we go to find the value function, the V. But we don't try to just take V as like average of all possible action. We know individual actions and where that led to. Based on that, we try to find the optimality. So same concept is the TD learning, TD target minus previous estimate, TD error. Okay. This could be also written this way, the state action. Expected immediate reward for a state given an action is expectation, that is all possibilities, right? So plus discounted, whatever scenario you go, whatever states that you go, times the values. Okay, so it's kind of like a futuristic discounted value. So if I am here and I take an action, okay, what reward I will receive? Well, I don't know. I know the action, but I don't know what reward I will receive. So the reward that you get from that action is average. It could be any reward. It could be 5, it could be 2. I know the action, but I don't know the reward.
Average over what?
Average all possible rewards. So this basically expected value with respect to the reward. If I'm here, 20% chance I will get $2. Okay? If I'm here and I do this action, 40% chance I get $6. Right? And 40% chance I get $3. What's the total amount of dollars I will get? 20% times 2 plus 40% times 4 plus 40% times 3. Right?
Previously, we knew the current state, and we knew that 20% we can take this action, 20% we can take the other action, but now we know the action.
We know the action, we don't know the reward of it here.
So how we know the probability of that reward?
So the reward part is that you go through the environment, right? You basically try it, learn it. So again, these are like, if it's a model free, we don't know what we end up with. So as we will see, we first start with a zero estimate for everything. And then we increment, which is, okay, let me try a step, see how much that action will give me. But in reality is that, I think we have this in an example here. Let's look at this example. So this is just a simplistic example. Let's say we have 2 estates, A and B. If I'm in A and I take action 1, I go to B, I get $10. If I'm in A and I take action 2, I get to C, I get 0, right? If I'm in A and I take action 3, I get $2. Okay. Similar for B. And then I have these policy matrices. If I'm A, there's 50% chance I will take action A. There is 30% chance I will get action 2 and 20% chance I will get action. It's like a chance that I take an actions. So the next thing here is that, does that make sense so far? So the next thing will be, well, I think we need to solve it then. So let's do that. So just do one of this. We pick one to close this loop. So we have, so there are 3 actions. I would say that there is if I am in A and I take A1, it's 0. If I'm in A and I take A2, it's 0. If I'm in A and I take A3, it's 0. If I'm in B and A1 is 0, B and action 2, 0, B and action 3 is 0. So at first we start, and let's say this is just random. We take an action, and let's say action, because we're starting from A, and we took an action, and it was A1. Okay, so where does A1 go? A1 goes to B. So we go to A1, we go to B. Our reward was 10. Okay, so now we want to basically use this knowledge to update that. So the formula we have, let's go here. QSA plus some discount. Let's see. Okay, this is 1 over NS technically. And this is going to be R discounted value of Q S prime. We got this prime A prime minus Q as A. Sorry, this went over. That's just a formula to have. So now I want to understand that what was the value of the state action value for this action given this state. Okay, or this state given this action. So QA A1. So this comes from my previous estimate, which was 0 plus a learning rate. What's the learning rate? So I took this action 1 time, so this becomes 1 over NS1, right? Times, what was the reward? 10 plus, what was the discounted of the future? So I go to B. That's basically what it says, right? What's the value of B technically? Well, 0 at this point, right? So because discounted times 0 minus the value of A at first is 0, so I get 10. Now I'm in B. Let's say from B I took action, where does it go to? Let's see, an action that goes somewhere. 2 goes to C. Actually, let's go to A so we can learn something. So let's go A1? Okay, so we do A1, and where does, actually, right here. If I'm B and I go A1, I go to A, what's the reward? 1. Plus 1. So here we get plus, so we get 0 plus 1 over 1, because I saw B for the first time basically, over 1 plus discounted value of A. What's the discounted value of A? 10, right? 10 minus the the value of the B itself, 0. So this becomes 0. Let's say gamma is 0.9, right? 0.9 times 10, 9 plus 1, 10 again becomes 10. Now let's say from A you take the same action, you go to B again. Okay, so Q A1. This time becomes, what's your previous estimate? 10 plus, what's your learning rate? 1 over 2 times reward 10 plus 0.9 times, what's the value of B? 10 minus 10. So this becomes 9 plus 10, 19, 9 4.5, 14.5, and so on. So you keep sampling and stuff like that, just update these values. You get to the point that you know what's the optimal basic action and what's the optimal basically state that you can reach.
We have those probabilities.
I mean, not in most of the models now. It's just a simplistic scenario.
It's like
So let's say I don't know this probability of things happens. What do? The simplest thing comes to my mind. I just let the agent do, and I count how many times it automatically, like I count what happened, how often happened, and from that I start creating the chance of taking actions. Right. So it all depends on also what you try to do. You might try to enforce some dynamic that if you are here, you need to do this, or just want to be like, I don't know, I want to learn it. So I'm just going to finish the sentence on this. Let's go back here. So this makes sense, this part? Okay. So just to connect this to value function is that the action value, if you think about it, a state action basically function, the Q function. So Q function basically tells you that how much reward, or basically overall, how good is this if you're in this state, take this action, right? Then the value function, so a state function is, a state action is for one action, correct? If I take this action, how good is this? Value function is not about one action, it's like all possibilities. If I take this action or that action or all of those. So you pick the Q, do weighted average over all possible actions. Expected value over the policy, that means any possible actions. I take a right, based on the right, I learned if you go to right, you are 10. If you go to left, you are 14 and you are 20. So I have these three values. There are three possible actions, for example. Also, I know what's the chance of taking each of those. The chance times this plus the chance times this plus the chance, that becomes the weighted one, right? So that overall gives me the value function for that state, all possible actions. Then there is a relationship between Q and value function, reverse. Because if you think about it, the Q basically says that what is the, like if I'm in the, let's put it here. So if I am a state S and I want to take action A, okay, under certain policy, that gives me a reward and gives me a discounted of the future, right? But under the certain policy. Right, so again, it's like a policy is the important part. So it's like a state action, sorry, value function is with respect to a state action. A state action is with respect to immediate reward and the next state that you go. And the same thing, next state is, this is the same thing. This line 3 and line 1, that's the same thing, summation over all possibilities. This one is written with respect to S prime, this one is with respect to S. So 1 and 3, they are the same thing. The second one is just with respect to actions, okay? And if you have the optimal Q, you can find the best policy by picking the policy that gives you the action that gives you the maximum overall Q, basically, Q function. Because again, if you think about the Q basically says that I'm here. What is the best action that I can take? But it doesn't say the best action based on the action. It says the action based on the feature also, like there's a bootstrapping. So if you know that, and you know all the possible actions, you have seen all the possible action, if you want to make a policy update, that means you want to update your mental model. Next time I'm here, what to do? You just remember across, every time I was here, I earned this much based on the action. So I picked the action that always gave me the best result. That becomes the policy, optimal policy, basically. All right, I'm going to stop here. So let me see. We have